Good morning, everyone. It's a pleasure to have all you here for the Quantum Battles in Attoscience 2023. I'm just realizing it was much easier to run it from my kitchen, actually, but we really appreciate your effort of coming all the way to London and taking part on this. This is the first live version of this workshop, and the key idea is to make it not only very informative and bring cutting-edge physics for you, but to make it also very educational and bring early career researchers to the forefront and discuss areas of tension in attoscience. So our first day, in fact, is the AttoChem day. So you think the AttoChem cost network for supporting this first day of the Quantum Battles here at University College London. And because it's the AttoChem day, our first speaker is the AttoChem boss, who is Professor Fernando Martin from Madrid. And he will talk about imaging and controlling electronic motion molecules with attosecond time resolution, namely attochemistry, which is a big topic on this first day of the conference. So thank you so much for coming, and we are ready to start.
Thank you, Carla, for the introduction and for organizing this meeting. And I'm very happy to see a lot of faces and known faces here after, after some time. And I will speak about, I added the word theoretical at the beginning of my presentation because for obvious reasons, I'm a theoretician, so I will focus more on the theoretical part, but emphasizing why these theoretical tools that are in place can be useful to develop and interpret experiments in attochemistry. So, I don't think I have to justify why we need attoseconds in chemistry. As you know, nuclei move electrons move very rapidly in the scale of the attoseconds, and this motion is much faster than any other motion in the molecules, like vibrations or the way you break bonds or you form bonds. This takes much longer, but you should not forget that the way a molecule breaks or vibrates is entirely dictated by the electronic motion. So if we are able to visualize this motion and eventually to control it, then we'll be able to manipulate the chemical response of any molecular system. So I will discuss basically two schemes that have been used experimentally to visualize these electron dynamics in molecules. One is a pump probe, in which you use an attosecond pulse to ionize your molecule. You will always ionize it because these attosecond pulses are generated in the extreme ultraviolet or soft X-rays. And then you come later with another pulse, a probe pulse that is delayed with respect to the former pulse, and will take a picture of whatever electron dynamics is going on in the molecule. And then you repeat this by delaying further your probe pulse, and then you take another picture at a later time, and so on. You repeat these several times, and at the end, you get a sequence of frames that give you the movie. Of course, the movie you will get doesn't look as nice as the one you see here. Ideally, this is what you would like to see directly, but what you get is a spectrum. And then you see, how this dynamics reflects in a measured spectra. The other scheme that has been widely used in this business is RABIT, reconstruction of the beatings by interferences of two photon transitions. I will not describe this in detail because there will be other talks today speaking about this, but basically here, instead of using a single attosecond pulse, you use a train of attosecond pulses, and you overlap this train with an infrared pulse, and you vary the delay between them. And from this, you record photoelectron spectra in which, they provide what is called the two-photon ionization delays. Okay, so a very important point is that, in either scheme, you don't have monochromatic light because due to the short duration of the pulses, you have a very large bandwidth. So you have photons of many different colors, and that means you can ionize your molecule from many different states, and what you produce at the end is a coherent superposition of states. You don't excite or you don't produce the molecular cation in a single electronic state, you produce a coherent superposition of electronic states. And this is very important. Okay, so since we are speaking about coherences, then obviously we have to use a quantum mechanical description of this. And we should be able to describe ionization, which means we have to describe unbound electrons. And we have to describe also how these electron dynamics is coupled to the nuclear dynamics, which eventually can modify the coherences that you induce with your attosecond pulses. So this is what one has to solve, time-dependent Schrödinger equation. And you have to do it in the time domain, of course, because we are talking about time here all the time. And this equation is super hard to solve, as you know, and it cannot be solved numerically except for the H2 plus molecular ion. So there are different methodologies, and I will start from the most accurate one that consists in expanding the time-dependent wave function in the basis of eigenstates of the molecule. And these eigenstates contain both an electronic and a nuclear part. So these are products of electronic wave functions and nuclear wave functions. And as you can see, we have electronic states representing the bound states of the molecule, but we also have to describe the ionization continuum and all resonances that are embedded in the ionization continuum. This is ideally what you have to do. And that's why you have three groups of terms here. And every group is, as you can see, it contains the nuclear part of this quantum motion of the nuclei. Okay, and then when you plug this equation into the time-dependent Schrödinger equation and you project it into the eigenstates, then you end up with a system of coupled differential equations in which your unknowns are these coefficients that depend on time. But for that, you have to calculate previously all the electronic and nuclear states that are in this expansion, and you have to calculate all the couplings, you know, between these states induced by the laser field, or due to non-adiabatic effects, or eventually they are not exactly eigenfunctions to the Hamiltonian. You should also take into account that you should include these couplings through the Hamiltonian. And what is very important is that because we are in pan-probe schemes where you ionize and there is a second photon that is absorbed when the electron is in the continuum, you also have to deal with the couplings in between continuum states, which is not that easy to calculate in general. So this is ideally what you should do, and this has been done several years ago by us. But let me say before I show you some examples, the critical part here is not to calculate the bound states, which you know, is something that you can do by using standard quantum chemistry tools. It's not a problem either to calculate multiply excited states or resonances because they look like bound states. They are quasi-bound states. So, you know, they have a strong bound character. So you can still use standard methods in the literature to represent those states. The main problem is to represent the continuous states of a molecule in which you have several centers. This is not that straightforward. And for that, you need specific methods that are not, you know, available in commercial packages. And you also have to calculate the nuclear wave functions, you know, which is trivial for diatomic molecules or small polyatomics. But when you go to larger molecules, this is as difficult as calculating, you know, the electronic states. So these are the things you have to do. And this was done, as I said, a few years ago. And for the H2 molecule, which is something you can afford. And in this particular example, this is, to my knowledge, the first example in which attosecond tools were used to image electron dynamics in a molecule. In this case, the simplest one, H2, and the experiment was performed by Mark Bracken and Mauro Nisoli in Milano. And later on, this tool has been used to investigate different processes in this molecule. For instance, in the context of rabbit, this is a more recent work. But I don't want to discuss this because these are old works that showed the power of theoretical methods in order to interpret, you know, experiments that in those days were difficult to understand. Now, there are other alternatives still preserving the accuracy of your methodology, which is the so-called Born-Huang expansion. So if you compare this expansion with the one I showed before, you will realize that here I have removed the coefficients that depend on time, and I have removed the nuclear eigenstates. And I have replaced them by some functions that depend both on the nuclear coordinates and time. So now my unknowns are not the coefficients that I had before. Now my unknowns are functions that depend on the nuclear coordinates and time, as I said. And when you put this into the time dependence equation and you project, then you end up with a system of coupled differential equations where, you know, in addition to the first derivatives with respect to time, you have the action of the nuclear kinetic energy operator on these functions. So let's say this method at the end is equivalent as the previous one. The difference is that, well, this is more easy to write because you only have to calculate the electronic wave functions. You don't have to calculate the nuclear wave functions. But here you have to calculate them as they propagate in time. So this part is much harder to resolve than the previous one I showed. But at the end of the day, the computational effort is the same. Basically, these are very expensive methods, and the bottlenecks are exactly the same. You have to calculate exactly the same matrix elements, including the continuum ones. And so, you know, the same limitations that I mentioned before for the spectral method are applicable.
I think that's a fire alarm.
Fire alarm. Yeah.
So everything's working again?
Yes, everything is working again.
Okay, great. Okay, so I was saying that, you know, alternatively, you can use this Born-Huang expansion that is very popular in quantum chemistry world, and it can be useful in some cases. Okay, but I emphasize again that these calculations are extremely complicated and very expensive, so you cannot perform these calculations for very large molecules. So again, I emphasize that the bottlenecks here is to calculate the electronic continuous states of molecules and the nuclear wave functions when you have many nuclear degrees of freedom. Okay, same problem as before. So we applied this methodology very recently to investigate rapid in the nitrogen molecule. And this was published this year. And this work was inspired by a pioneering experiment performed by Hessler and collaborators many years ago that remained practically unexplained until today. And the reason is that in this experiment was a rapid experiment. You know, they were using harmonics like the ones you see here in this picture, in which they were hitting the molecule here just above, you know, the second ionization threshold in a region that is full of Feshbach resonances. So what you can see here is these are the three lowest ionization thresholds of nitrogen. And all the other curves you see here, some of them have a larger width. These are Feshbach resonances. And the width of the line shows you the width of the resonance. And as you can see, when you come with these harmonics, then you hit these Feshbach resonances. So in addition to directly ionize the molecule, you populate these Feshbach resonances. And Feshbach resonances take a while to eject an electron. So during the time they take to eject the electron, the nuclei move. So if you don't correctly describe the nuclear motion, then you will not be able to represent what is going on in the experiment. And that's why, you know, this experiment remained unexplained for so long. But with the theory I showed you, we were able to perform calculations for this situation by taking into account that these Feshbach resonances decay while the nuclei are moving by using this Born-Huang expansion I showed you. By the way, these resonances have been observed previously in synchrotron radiation experiments, and you see very nice peaks. And this is a theory curve produced by us showing that, you know, the resonances are well described. But here, you know, in this experiment, they were populating basically this region. So this region here. And then, of course, when you come with, you know, you take into account the infrared and you come with another infrared photon, the signature of these resonances will be imprinted in the measured photoelectron spectrum. So what we did was just to focus on this region. And this is the photoelectron spectrum you get when you only use the train of attosecond pulses. And well, what you can see, you see different harmonics. In this case, the high energy resolution of the experiment allowed to resolve the final vibrational state of the N2 plus cation. And you can see that there are different series. Every peak here corresponds to a final vibrational state. And you see that, more or less, these series follow more or less the same structure here, the same here, big peak followed by shoulder here. But when you go to very low energies, these patterns change. Instead of seeing a single peak, you see a single peak plus 2 or 3 additional peaks here. And this thing changes also completely. And this is the region where photoelectrons are very slow. So the electrons, take a long time to escape. And this is where nuclei move substantially. And so the reason why you see that these progressions are different is because of the coupling with the nuclear motion. And this is what the theory was able to describe, which compares fairly well with the experiment. And of course, well, we also included the infrared field to calculate the sidebands. And this is the difference between the APT and the APT plus IR spectra compared to experiment. And you see that more or less this reproduces the experimental results. So of course, if you have the rapid spectrum, then from the calculated sidebands, you can get the sideband phases. And as you can see here, in the case where you are populating the resonances, you see a huge variation of the phase. While when you are not populating resonances, you see that the changes in the phase are smooth. Okay, so I think the message is that even in simple molecules like N2, and this is very simple, still, you want to reproduce what is going on at low electron energies or in regions where you have long-lived resonances, you have to couple electronic and nuclear motion from the very beginning. And you have to do it in the appropriate way. Otherwise, you will not be able to represent these effects. Okay, this is very good for small molecules, as I said. But when you increase the size of the molecules, then you have to start doing approximations because you cannot use this methodology anymore. And so the possibility is that if you are really studying something that happens in a very short time interval, let's say a few femtoseconds, 4, 5, 6 femtoseconds, you are only interested in this region, then you can assume that maybe your initial nuclear wave function is not going to change much with time. So you can say, okay, let's freeze it. And then what you do is just to assume that all the dynamics will be purely electronic. Okay, then you have to solve the time-dependent Schrödinger equation, but only for the electronic degrees of freedom. And then you will have these two terms. Of course, since we are assuming that nuclei barely move during the interaction time, then we will not have access to resonance states, because as I said, if we want to describe resonances, we have to allow the nuclei to move. Okay, so if we don't allow them to move, then we should forget about problems in which resonances are populated. At least, very narrow resonances, which are the ones that live longer. So then you have to calculate, as usual, the transition amplitude with these things. This is a calculation that is expensive because it requires calculating this, solving this equation, for different values of the molecular geometry. And then you have to calculate only the initial nuclear wave function. And of course, the final nuclear wave function that you have to plug in here in order to get the transition amplitude. But you avoid calculating nuclear wave functions for all the intermediate states. Okay, this is sort of a diabatic approximation that we tested also in nitrogen. And so these are experiments performed by the group of Anne Lullier in Lund. And here you see the theory and the experiment. You see nice sidebands with oscillations. And from these oscillations, one can extract the 2 photonization delays. And this is just an example of how these things work for different final vibrational states. And you see that, whenever you hit a region where you have, in this case, you have a very broad shape resonance, very broad, which takes only 70 attoseconds to ionize. So in this case, you can assume that the nuclei do not move. So it's not the case I showed before. But you see these huge variations in the experimental data that are reproduced by theory, although shifted in energy. And the reason is that in those days, this was an earlier work. The methodology we were using to describe the electronic structure of the molecule was less sophisticated than the one that I showed you before, or for the rabbit at lower energies. So again, this is a tool that is useful when you are far from narrow fastback resonances. It works. We have also checked it in more complex molecules like CH4 by reducing a little bit the dimensionality of the nuclear motion. And this is done in collaboration with a group of Hans-Jakob Werner. And where they were able to get rabbit spectra for the non-dissociative part and the dissociative parts. So they were able to do this by detecting in coincidence electrons and molecular ions. And from this spectra, then they were able to extract relative photoionization delays. Here is dissociative versus non-dissociative. This is for the two isotopes that I showed before. And on top of this, you can see the results of the calculations. And what is remarkable here is that these differences are extremely small, of the order of 20 attoseconds or less as we increase the photon energy. And this is captured by the experiment, but it's also very well reproduced by the theory. And the interesting thing is that here, even at this short time scale, the ionization delays are sensitive to what is left behind. So if you don't break the remaining molecular ion, then you measure a given delay. If you break it, you measure a bit longer delay, which is not totally unexpected because, when the molecule breaks, it becomes larger, let's say. So in principle, the electron that escapes will be more affected in principle. But, well, this has been quantified. That's an interesting point. Now, if we go to larger molecules, which is something that we want to put chemistry, we would like to go to even larger molecules, then you have to start doing more approximations. And the very first one is that you have to separate the different steps. So far, in all the examples I showed, theory didn't separate the pump, the probe steps, or in the rabbit, we included both the XUV, the infrared, all at the same time. So there were no approximations. But if you go to larger molecules, there is no way to do this. So what you have to do is to separate, to split the problem in different steps. The first one is just to describe the ionization. Then you have to describe the coupled electron nuclear dynamics that follows the pump step. And then you have to describe the interaction with the probe pulse. And you can do these three things separately. And then you have to design strategies to switch, to match the different steps. And if you are interested in measuring ions, you should also describe the coupled electron nuclear dynamics after the probe step. So how you can do that? Well, the very first thing is that you should start forgetting about quantum mechanical descriptions of nuclear motion, because this is extremely heavy. But for the time being, let's assume that we only want to describe the pump step. So we shine a molecule with an attosecond pulse. And so we will follow a methodology that is similar to the previous one, kind of a diabatic approximation, but now instead of using the true nuclear wave function we have initially, we will simply sample it in a few specific geometries. That this sampling is usually a Wigner distribution. So why, you will wonder why you do that, because it's just the wave function for the ground state. But even the nuclear wave function for the ground state, when you have many degrees of freedom, is a huge problem. So you just sample these initial geometries, And the rest is the same. You have to solve, the time-dependent Schrödinger equation for the electronic motion. So the only difference with the previous case is that instead of having here a true nuclear wave function for the initial state, you just sample it. Okay, so, and then if you want to calculate the free evolution after the pump during a very short time interval, then you can say, okay, I don't care about nuclear motion, I forget it completely. And then what you have to do, because this is a step that is separated from the previous one, you assume that the ionized electron goes rapidly away from your molecule. So this excludes problems in which the ejected electrons are very slow. And then what you do is to trace out a continued electron by using the density matrix picture. And then you can calculate the n-1 electron density as a function of time. So this is precisely what was done in 2014 in collaboration with a group of Mauro Nisoli to get this movie on the phenylalanine molecule, but this was not sampled. This is just what happens at the equilibrium geometry. So in those days, we were not able to include the full Wigner distribution because it was extremely expensive. Nowadays we can, as we will see later. And we did it also for tryptophan. And well, these were, to my knowledge, the phenylalanine case was the very first example in which, again, attosecond pump probe strategies were used for a molecule of this size. So now what happens if you include the different initial geometries? So this is recent work that we are doing in collaboration with the people at LCLS and with some participants in this meeting, as you can see, in which the aminophenol molecule, is ionized by an attosecond X-ray pulse. And so we perform calculations for, a Wigner distribution of geometries. And here you can see the different geometries that you are considering. So we consider around 100, Now you compare the sampling that you get with the 100 geometries. This is the blue area here. Well, it's not very smooth compared to the real geometry distribution that you would have if you had a real nuclear wave function, but still it captures more or less, what happens for the different coordinates. This is the dihedral angle. This is another angle. So you can make plots of this for every nuclear geometry. Now, when you do that, this is, well, for the equilibrium geometry, you get a nice movie as the ones I showed before. And this is the the electron dynamics you would obtain when you plot, for instance, the charge around a given group. Okay, for instance, this one here, or this one here, or the ring. The three colors correspond to three different regions. And then you see that this charge, as you can see here, oscillate with time. And these oscillations remain there forever. But when you just average over the initial geometries, all the existing initial geometries, you see that these oscillations still remain at very short times, and after some time they are strongly damped. They don't disappear completely, they are still there, but their amplitude is much smaller. So this is the effect that one would expect. So you are performing a pump probe experiment on this molecule. You should be careful and probably focus, if you want to look for electron dynamics, you should probably focus on the very first femtoseconds. Now, the very last step is to calculate the photoelectron spectrum that you would obtain if you probe this, for instance, with another X-ray attosecond pulse or with an XUV. We did this in phenol, which is a smaller molecule. Aminophenol is more complicated, so the less atoms you have, the better for you, for your calculations. But we thought that this was quite similar. So again, we calculated, the Wigner distribution of initial geometries. And again, you see here, the charge dynamics around the oxygen atom, when you just consider the equilibrium geometry or when you average over the initial geometries. And the same thing, as I said before, is here. You see that the oscillations remain, but they are damped after a while. And now you plot the photoelectron spectrum here for the equilibrium geometry. You see that the photoelectron spectrum here, you see the kinetic energy of the electrons versus the pump probe delay. And you see that these changes, there are oscillations at all kinetic energies of the electrons, but if you integrate over kinetic energy of the electron, you see that the oscillations remain. And they follow more or less, what you have here. Now you average over the initial geometries, then you see that the oscillations are damped in the photoelectron spectrum. But again, you see some oscillations here at very short times that more or less follow, what you have in the evolution of the charge. So this calculation was performed by assuming that the nuclei did not move at all during the pump and the probe steps, because we said, okay, since everything is going to die after 5-6 femtoseconds, the nuclei will not move substantially. But in some cases, this might not be enough, and you should include nuclear motion. And what you should do, and this is my very last slide, is that, well, when you do that, then you should allow the density, I mean the orbitals you have here to change in time, because there will be non-adiabatic transitions between the different states that are involved in the coherent superposition you generate with your attosecond pulse. And so you have to do it classically. And for instance, we have implemented a methodology that is based on the trajectory surface hopping approach that is well known in quantum chemistry, but has been adopted and modified slightly to account for this problem in the ionization continuum. And hopefully this is the methodology that will allow us to get results as the ones I showed you before by including the nuclear motion in this system. So in conclusion, full description of coupled electron nuclear dynamics induced by attosecond pulses and probed by second ultrasonic pulses is nowadays possible in diatomic molecules and small polyatomic molecules with high accuracy. When you go to larger molecules, you have to rely on kind of adiabatic approximation, in which you assume that the nuclear wave packet you have initially doesn't change during time, but still you preserve the quantum nature of the nuclear motion. And finally, for much larger molecules, then you have to start doing approximations in which nuclear motion is treated classically. And let me acknowledge the people who did this work that I have shown here. Some of them are no longer in the group. And of course, I'd like to acknowledge the AttoChem cost action that is supporting this meeting and many other things, and all the funding agencies that allowed us to develop this work. Thank you very much for your attention.
Are there questions, comments?
Fernando, let's.
Yeah.
Oh. It's a really great talk.
Yeah,
really great talk. I guess I understand that it's exceptionally difficult to include the nuclear dynamics, and it's also kind of obvious that the nuclear dynamics are going to matter. Is there some sort of cheap version of doing this where you just involve, say, the hydrogen dynamics around the site that you're probing? So I'm thinking of the aminophenol. If one were just to calculate what's happening with the proton near the oxygen site, would that be some way of doing something that could actually be consistent with the rest of the approach, but at the same time perhaps explain experimental observations better?
We don't have too much experience. I mean, these results I show here are not published yet. Just to give you an idea.
Well,
so,
this afternoon I'll show some results from the aminophenol that you were modeling, where there is a strong hint that perhaps the proton near the oxygen site is moving away very fast.
Yes, this is moving. But to give you, we already have some preliminary results for this by including nuclear motion. Preliminary, okay? So I don't want to put my hat on fire, okay? So that, yes, indeed, this thing moves in a significant way. But most of the charge dynamics you see involve the oxygen atom, not the hydrogen. So the oxygen removes charge from the hydrogen, so the hydrogen has, but if you are interested in the electron dynamics in between the oxygen and the ring and the other groups, this motion will barely affect these dynamics. In fact, we have preliminary results showing that the spectra we get for this molecule, when we include the nuclear motion, is not that different from the one we get without including it during the first 5 femtoseconds. Which is, in my opinion, the logical time interval to look at because of this region. So, I mean, if somebody wants to perform an experiment here, well, it would be much harder because...
Yeah, on the other hand, it does depend on the molecule.
Exactly.
And there are some molecules where the geometry averaging is not going to kill off the coherence.
So, let me, as a general recipe, this is probably what you want. If you have hydrogens around, yes, of course, hydrogens move very fast. Now, if you choose molecules in which the hydrogens are barely involved in the dynamics, in the charge dynamics that you generate, you are safe during, let's say, 10 femtoseconds as a rule of thumb. Okay. Now, you choose molecules in which the charge dynamics involves hydrogen atoms, then you should take into account nuclear motion from the very beginning. So my recommendation to experimentalists in this audience is please choose molecules in which you don't have too many hydrogen atoms to start learning something. Then when we understand this, yeah, go ahead and put as many hydrogen atoms as you want.
Okay, are there further questions? Would anybody like to ask something? I think we are fine then. So thank you so much for this really nice talk. And we're moving to our next speaker, who is Justas Terentjevas. He'll talk about driving and imaging Achiral-to-Chiral phase transitions, and chirality is a big topic on this first day of our conference. So yes, please. And I'll wow. Okay, so ready to go. Thank you so much. And if you need, yes, you need this. And this should be the clicker.
Thank you. Is it okay? Okay, thank you. So my name is Justas. I'm currently just finished my master's at Cambridge. So today I would like to present my work on that we did at Imperial in David Ayuso group on imprinting chirality in hydrogen. So first, let's talk about what, oh, sorry. Oh, it's turned off.
Okay.
Yeah. No, it was turned off, so now it should be okay.
Is it okay?
I don't know, it doesn't like well, I can just use the
You had the clicker, right? You can use this one.
yeah. Okay, yeah. So what is chirality? So the easiest way to imagine chirality is just to look at our hands. You know that they're mirror images of one another, but most importantly, there's no rotation or translation that can be done so that to perfectly align on top of each other. Now, the main thing we are interested in is chiral molecules, and in fact, nature exhibits what's known as homochirality, meaning that only one enantiomer or the chiral partner is present. Now, this makes the ability to correctly distinguish one enantiomer from another crucial for example, drug development. Now, so far, we can, in loose terms, call this a natural chirality, meaning that things are chiral in their ground state. What we are interested more is in what we call a synthetic chirality, or artificially created one. But before we go into that, it would be nice just to talk about how chiral matter interacts with light. So a very important feature of chiral matter is that it has very similar, almost identical physical and chemical properties within enantiomers. But there's one caveat, and this comes from the fact that it has to interact with something chiral as well. So, for example, light. And traditional spectroscopy methods use circularly polarized light, which traces a helical structure in space. And the chirality here is enforced by the pitch of the helix. But because the pitch of the helix usually at the scale of wavelength is several orders of magnitude higher than the molecular size, it makes the chiral interaction very inefficient. So, but of course we can do better, and we can, instead of using helix in space, we can create optical fields that actually trace the electric field traces a chiral structure in time. And this was proposed by David, Andres, and Olga a few years ago. So here we have, I don't know if I can, yeah. So here we have the Lissajous figure of such field. So the tip of the electric field traces this chiral structure in time. Now, the main thing why this is so efficient is that the electron dynamics induced by this locally chiral light happens at the same scale as the molecular size. So this gives a very efficient chiral discrimination. Now, what we instead of just distinguishing different enantiomers, what we use the slide for is just to imprint the chirality in hydrogen. So how does this work? So it was first shown by Andreas and Olga that within hydrogen, we can have chiral superpositions of electronic states. So in order to create them, we need at least two different angular momentum orbitals. And one of the possibilities is shown here. So although it may seem symmetrical, the phase is actually what is enforcing the chirality. So there's no plane reflection plane that could leave the system invariant. Now, how can we actually reach those states? So a few years later, it was shown by Nicola and co-workers that by using a non-collinear setup with circularly polarized light, we can actually create a locally chiral field, which is also shown on the right hand side. And this locally chiral field is very similar to what we saw above. Before, sorry, is sufficient to excite electron to one of the chiral superpositions. And of course, the handedness is encoded in the photoelectron distribution. Now, in our work, what we try to do is show whether this can be done in an all-optical setup. Can we use light to both excite the electron to chiral superposition and then observe it using only light? So, so what we did, so we took the locally chiral field that has a one elliptically polarized component at omega, and then orthogonal to that linearly polarized component at 2 omega. So on the left, we see the Lissajous figure of one cycle, and this this field is both locally chiral and globally chiral. Now, of course, theory is as good as it can be tested. So how can we actually make it experimentally? So a very common way is just to use a non-collinear beam setup. So here we have two beams carrying two frequencies orthogonal to one another, and in the overlap region we get the Lissajous figure on the left. So what we did, so we took one of the light enantiomers. It's on the top right corner, and then we solved the Schrödinger equation. So here we have the total induced dipole moment, and of course we can see the very strong linear response, because of course we use a very strong laser pulse. So this is nothing too I guess exciting, but if we look at the edges, we can start to see some deviations from the higher order effects. So we can see if chirality is also somehow encoded in that. And if we remove the fundamental frequency, we're left only with high frequency components. So far from these two figures, we see that electron is moving in chiral trajectories, both at low and high frequencies. Now, the most important thing is, even when we turn off the laser, electron is still moving in chiral trajectories. And and this is the dipole moment that is left when the laser is gone. So if it looks like a wool ball, but if we try to trace one of the strands, it looks like a ellipse, which is processing around several different axes. Now, also very important thing is that we can actually control the handedness of the hydrogen, and this can be done by changing the phase of the light field. So, for example, if we take phase difference of pi, we get an opposite enantiomer, both light and then the induced dipole. And of course, everything carries on with with opposite handedness. So, in fact, we have something that is chiral and can be controlled. Now, a more quantitative analysis can be done on looking at time frequency plot. So here we have the harmonic order, then we have time. So here shows what happens at different times in frequency domain. And of course, here is the highlighted strong linear response. Of course, we are more interested in what happens beyond. So in higher order harmonics, we also see this tail that is hanging just when the laser is turned off. So this tail is actually what's creating the wool ball that we see earlier, that is imprinting the chirality. And the oscillations are actually between ground state and the first excited state, and ground state and the second excited state. So we know where this is, more or less where this is coming from. Of course, we can do better. We can go to orbital mechanics and see what happens there. So the easiest way is just to try different combinations and see what this results in. So for example, if we take the ground state and the P0 state, which can be excited using linear polarization, that it is present in our light field, then it also creates a linearly polarized dipole moment. And here it is the electron density and how it changes in time. Unfortunately, this is cylindrically symmetric, so nothing chiral. We might ask what happens if we take P plus instead of P0. Well, then we have something that is actually rotating, so maybe this is chiral. Well, it has a planar symmetry with respect to the screen, so still not good. Well, the next best thing, maybe we can just combine the two and see what happens. Well, then it just still circular polarization, but then tilted at some angle. So not chiral. What we are left with is the maybe second excited state. But if we do the same analysis, we see that it's just tilted at different angles and rotating at different frequencies. So far, nothing chiral. But if we try to combine everything that we have, we actually get something that looks very similar to what we saw in the dipole. It is two circular polarizations at different tilts, and of course rotating at different frequencies. And if we try to look at how this evolves in time, it actually looks something similar to just two different rotations and at different angles. So we shown that we can actually imprint chirality, and we looked at how this, what are the underlying mechanics. But then to make this more concrete, the next step is to just check whether this also holds in the far field regime. Well, we expect this to hold because we have a globally chiral field. So we hope this should be also enforced in far field. Okay. And of course, the conclusion. So just to summarize everything, we have our, we've shown that we can use the locally chiral light to induce chirality on something that starts as a chiral. And then, of course, to improve our, or not improve, but just to check whether this holds in the far field. And of course, we need something that to characterize the imprinted handedness. So these are work in progress. And of course, just to acknowledge everyone who participated in this project and helped to prepare for this talk. So thank you very much.
Well, thank you so much for your very interesting talk. Other questions, comments? No. Okay, here.
Can I ask about the chiral trajectories that you plotted? Kind of how did you compute this, and what exactly? Yes, like the kind of rugby ball thing.
Yes, the dipole.
Yeah. So what did you use to compute this?
We just looked at the. We just solved the Schrodinger equation for the transition. I mean, we just sandwich the two and then calculate numerically.
Yeah. So it's the dipole.
Yeah, it's a dipole.
Okay, but it's kind of plotted at different. What exactly is plotted to make this chiral shape? Yeah.
I mean, why this? Why
yeah,
this
like the
makes
colors,
a chiral?
for example.
Oh, sorry. Yeah. So the colors is just dipole moment. So it should be a 3D structure. We can imagine X, Y, and Z. And the color is encoding time. So how this changes in time. So
okay. Okay. Yeah, that's.
If we go from red
cool.
to blue, this goes further in time. So this is how it changes.
All right. Yeah. Okay, that's very nice. Thank you.
Yeah, sorry about that.
No problem. So what would be your next step for this work?
Yeah, so this summer we'll try to make it work in the far field and then somehow characterize the chaotic thing more a bit, yeah, something with maybe how can we see different enantiomers, because we can change the phase and then see get infinite number of different enantiomers, so we need somehow to characterize those, but it's still a work in progress, so we're trying to come up with something. So if you have any suggestions, it's very welcome.
No worries. So thank you so much. And our next speaker is Thomas Rook from UCL, and he is going to talk about exploring symmetries in ultrafast photoelectron holography with two-color linearly polarized fields. So this is in a way going back to basics, but using also some nice group theory. So let's make a share. Challenge. So ready to go?
Yes.
Yes. Do you have a clicker? If not, you
I
can
mean,
use
the
it
clicker
here.
wasn't working last time.
Yeah, because I have a
Oh,
very
I
clicker. I don't know what happened to my clicker.
I don't know where it's.
Anyway,
Okay, this is the point. Is that okay?
things should be working. and
It's
have-
okay. Don't worry.
Yes.
I'll use the mouse.
So
Oh, thank you.
I have.
Just remember.
We have 3 clickers. And
One is connected.
okay, but don't worry. Yeah, but thank you. All right, so let's start.
I'll just use this. Yeah, it's fine.
Okay.
Okay. Hello. I'm Thomas, and I'm a student in the group of Professor Calafaria at UCL. Thank you to the organizers for letting me give a talk about exploring symmetries in photoelectron holography with two-color linearly polarized fields, and it's based on this publication down the bottom left. Okay, brief overview. Just start with some motivation, then talk about linearly polarized fields and what symmetries can exist, and then just an application to ultrafast photoelectron holography. Okay. So obviously, symmetry has been used in physics for a very long time, all over physics really. But there's some examples of, well, an example here of a use in attoscience, and then some others where recently we've had, with kind of the desire to use tailored fields to do some sort of sub-femtosecond control, an increase in interests of looking at symmetries to try and understand those slightly better. Question you could ask is why do you want to look at the symmetries? So why symmetry? Okay, so in the examples on the previous slide, they used sort of the dynamical symmetries of the field to derive selection rules for the high order harmonic generation. And so that's one reason you might want to look at symmetry. It can just help to simplify calculations, so you can avoid calculating something twice, or you can have some sort of neat cancellation. Sorry, so symmetries of the Hamiltonian are going to lead to conserved quantities. That's going to be really helpful if you want to, just get some physical intuition about the problem, or reduce this dimensionality that you need to actually consider. Okay, you can use the symmetries of the problem to make all sorts of qualitative predictions about the solutions that you're going to see. And then also it can be interesting when you break the symmetry, what actually happens, whether it's like a spontaneous symmetry breaking, or if you have like some approximate symmetry where like the asymmetric part becomes more important relatively. Okay, so how are we going to use the symmetry? We're just going to do a systematic study of symmetries that come about in linearly polarized fields, and then how that relates to kind of orbit-based methods. And we're going to apply these to study photoelectron holography. start with some transformations which are really useful in order to construct the symmetries that we want to, that we'd have in linearly polarized fields. So we have a time translation where by tau, where it's just shifting like that. You can reflect in an axis tau, like so, like this way, kind of see this, and or just like reflect in the kind of the field direction. So multiply the field by -1 really. Okay, so moving on to the symmetries that you actually see in a monochromatic field, there you'll see you have a half cycle symmetry where it shifts by half cycle and then it's flip. Reflect around the extreme of the field, or you can just reflect around the zeros of the field and then flip across the axis. And then, so I think that that's clear. But if you change the field, then which of these symmetries are retained and like how? Okay. So, okay, the simplest example really of a field, a periodic field's difference to monochromatic would be the bichromatic, but it's quite general in that depending on the parameters that you choose of this field, you can achieve like every possibility in the combinations of the symmetries that you can actually see for a periodic field. Okay, so the parameters that are important are the sum of R plus S, where R and S are the relative frequencies of the frequency ratios of the ratios of the frequencies of the constituent fields components. R and S, they're no common factors or anything. So if R plus S is odd, like we have in this case where R is 1 and S is 2, you either see none of the symmetries that you had in the monochromatic case, or you have just one of the reflection symmetries. So when the peak of the fields, should I point on this instead? When the peak of the fields line up like this, you get the reflection around the peak, and when the zeros line up, you get the reflection around the zeros symmetry. And so that all depends on the relative phase, right? So the relative phase is causing the second, the field with twice the frequency to move relative to the first. Okay, for the R plus S even case, this is the same, except you retain half cycle symmetry. And then any point where the peak lines up with the peak, it will also have the zero lining up with the peak, zero lining up with the zero, and hence you either have just half cycle symmetry or all three of the symmetries are retained in that case. Okay, that's okay. That's oh well. In a saddle point framework, so we'll start looking at studying ATI, above-threshold ionization with, namely this CQSFA, Coulomb quantum orbit strong field approximation, which has this amplitude here, where you're kind of summing over multiple semi-classical trajectories, which each contributes a complex amplitude to the final amplitude, hence interfere with each other. And you could, okay, there's a stability of the continuum trajectory part here. There's a ionization kind of prefactor, which is like this. And then you have the semi-classical action, which is given by this here, where you have to kind of do this integral along the trajectories as defined by these saddle point equations here, where, okay, you have these which define the continuum propagation of the electron, and you have this which defines the timer which is ionized into the continuum, really. This is going to be a complex time, given the tunneling is not a classical process. So, well, this imaginary part of the time, it really influences the prominence of the ionization around that time, really. For full, okay, then what we do in this publication here is we look at the explicitly at the general symmetries that you can get based on the field, what you get in the real part of the time and the imaginary part of the time of the ionization and how that affects the physics. But in this case, we'll look at a specific example of just the okay. Here we have for a omega to omega fields with a couple of different phases, we're showing the steepest descent contours on the imaginary parts of the I times the action. So what you can see here is really the symmetry of the real parts of the ionization time is heavily dependent on the symmetries that you have in the electric fields, like that. So these are going to line up like that down the middle and this down here, and you see what I'm saying. Whereas the with the imaginary parts of the ionization time, it really depends on whether, okay, if you have an asymmetric peak at the around the gradients around the peaks are asymmetric, or whether the amplitudes in the different cycles, half cycles, are symmetric or not. Depends, influences the symmetries that you see for the imaginary part of the ionization time. And so, just looking at some specific holographic patterns that we can see for different types of trajectory. We have a sort of a schematic here showing the type of trajectories which contribute to the different holographic patterns. And then here we have within the field where the ionization events occur for each of these kind of trajectories. So for omega to omega field, add these two different phases so you can kind of illustrate the differences. Okay, looking at the fan specifically here, we have these peaks are the same. So the prominence of the ionization in the two half cycles is going to be roughly the same. So this is going to lead to a good contrast in this band that we see for this phi equals 0. On the other hand, this is not the case for the phi equals pi over 4. So we're going to have this distinction. We have this difference in the prominence. So we therefore get quite poor contrast. If we then look at the spider pattern, we see that the ionization events occur in the same half cycle. So really the fact that these peaks are the same in this case means that the ionization to the right or to the left of the 0 here is going to be of equal kind of prominence. And in this case, you see that this peak here means that to the right, you're going to have far greater, it's going to be enhanced compared to the left where it's going to be suppressed, right? Okay, let me move on quickly to just, okay. Okay, you can see that here with the contrast being good above and the contrast being quite bad here. And it's also, well, shifted to the left in this case because of this asymmetry in the gradients around here. We get a bias in the initial momentum distribution, which propagates through the fact that these are relatively direct trajectory types, means that we get this kind of asymmetry is preserved in the final momentum distribution. Moving on to just look at the spider very quickly. We see, as we suspected, that this is suppressed on this side and enhanced on this side, and this is relatively even across the two sides of the parallel momentum. Clearly, though, the interference fringes have been shifted slightly, well, due in part to the asymmetry of the field around the peaks. Okay, so in conclusion, just more than that, just the half cycle symmetry is playing a role in influencing the photoelectron momentum distributions and the holographic patterns we're seeing. And even for the case of linear polarized fields, there's a lot more to be learned. And thank you for listening. And does anyone have any questions?
Okay, are the questions going? Okay.
Hi, thanks for the nice talk. So, you know, the symmetry choices that you kind of looked at the start, so you had these 3 different symmetries. I just wondered what motivated the choices to look at those specific symmetries? Was it like looking for some particular conserved quantities or?
Not particularly looking at conserved quantities. It was more just, Those are the kind of the only. Okay, you mean in terms of those particular transformations as opposed to some other?
Yeah, I mean, because I guess you could also have you could shift by a cycle as well in a monochromatic.
Oh, right. Okay. So it was. I guess we're looking at kind of holographic patterns where it's cycle interference. So the kind of looking at things happening over greater than a cycle was. I mean, it was also assumed to be periodic, right? As well.
So because you're looking at the intra-cycle interferences, you chose those specific ones. Okay.
Well, yeah, I guess.
But then I guess with the ATI kind of interference, if you look at the cycle shifting by a cycle, you can get like energy conservation. So in terms of conservation quantities,
yeah, okay,
maybe there's something you could see there as well.
That's it. That's a good point.
That makes sense. Thank you.
I mean,
I think
we're not that much, I think, looking at conserved quantities.
No, not so much, but
we're checking how one could, in principle, influence specific holographic patterns.
Sure.
By playing around with those symmetries, and those three, they're only present for monochromatic fields.
Yeah.
Yeah, or yeah, depending on the parameters of the field, something where you have R plus S being even, you get all three symmetries as well. But yeah, I don't. Sorry.
No,
that's clear.
And for us, an issue was that we wanted to go beyond only the half cycle symmetry, because people only focus on the half cycle symmetry, and there are other ones that play a role.
Also, like the half cycle symmetry, if you apply it twice, it's kind of periodicity, right? Is that no?
Yeah, it's the generator.
Yeah. But
okay, thank you. Yeah.
Okay.
But I don't. Yes.
Go ahead.
Okay.
So the first is, so there are other symmetries also for linear fields, like, you know, not dynamical, like just static mirrors and like continuous rotational symmetry.
Yeah.
So do those play a role in the spectra?
Well, yes, like yeah, they would do, and they've like, for instance, in this paper here on the this one, they look at this in detail, really, I think. So it's like, okay.
And
Yeah, but
So it's like
elliptically polarized, orthogonally polarized. Is that you asking linear, right?
okay, so for linear, I mean, it kind of generalizes, I think. Yes. Yeah.
For a linearly polarized field, there would be a fourfold symmetry, but this one is, I think, for the omega 3 omega OGC field, maybe. Because as we can see, the vector potential, the direct electrons nicely follow the minus vector potential. So that's the reason why we can't observe here a fourfold or even the twofold. It's only the rotational C2 symmetry present here.
Yeah, but concerning the other symmetries that we were discussing, first, if you look at the Coulomb distorted scenario, you don't have direct or scattered, it's all mixed up. Then you have the issue of the imaginary part of the times. So it's not only the dynamical symmetry in the classical sense. You need to see what is happening to the shadows. And then this is going to influence the contrast. And is going also to influence the tilt of the distribution. Yeah. So, for instance, in one example, you had difference in the gradient because you broke one symmetry, and the fan was tilted to the right or the left, but the fringes were sharp. And in the other case, you had a difference in symmetry where you broke the other one with regard to the maxima, and then you had no tilt, but the fan was blurred.
I mean, I guess in you will, of course, for linearly polarized, you'll have this symmetry flipping across this way, right?
Okay.
Okay.
Yeah, but we can discuss later on. We need to move on, but that is an interesting topic, and we wanted to have a look. So our next speaker is Adam Kirrander from Oxford, and he's going to talk about interference and ionization in ultrafast X-ray spectrum. And All right.
Does it work? Yeah,
Yeah, it's working.
good. Does this work? Oh, oh, okay, it doesn't.
It does. We can hear you.
Really?
Yes, it's showing, the signal is showing there.
Okay.
You definitely amplify.
You're
No, I
amplified.
just mean it doesn't change slides. That's what I meant. Sorry, but that's fine. I was hoping for
It
that.
doesn't?
No, that's all right. I mean, I can.
Speakers don't work.
And it doesn't work. Yeah, exactly. I know. It's fine.
But we're gonna fix that after the break.
Okay.
Okay.
I just give you a back.
Anyway, so let's keep on moving.
Yeah, thank you. Okay. Good.
Yes,
Okay, right. So yeah,
so
thank you very much. It's a really pleasure to be here. You know, big thank you to the organizers for inviting me. It's great to be in an in-person scientific meeting. Very, very exciting. I have to admit that there's no chirality in my talk, at least not any intentional. But hopefully we can find some interest. Anyways, I'll be speaking about ultrafast X-ray scattering from electronic wave packets, or at least going towards electronic wave packets. So okay, all right. So for about 10 years now, we've been increasingly obsessed with what one could do at X-ray free electron lasers, X-FELs. And so there's a increasing number of facilities around the world that can generate very short pulsed X-ray light of high coherence and very short pulse duration. So below sub-femtosecond is now achievable, and it's very, very photon intense light, which allows you to do a whole range of experiments ranging from imaging to spectroscopy. I'm sure that John Marangos this afternoon will tell us something about what can be done with spectroscopy. But for our part, we've been focusing on hard X-ray scattering. And in fact, that was part of the original sales pitch for these facilities. So the idea was that one could image single molecule proteins and so get around the whole problem of crystallization, which otherwise is necessary to amplify the signal and determine the structure. Now the sort of complication with that is that to get sufficient scattering, you need to ramp up your intensity. And if you ramp up intensity, then you get more and more competition to the scattering from photoionization from the X-rays. And that's a very strong radiation damage process. And so you're turning your sample to plasma. And the idea is that if you have a short enough pulse, you can essentially, the structure remains practically intact. So you get enough sensible diffraction information before it all disintegrates. Now, one way to get around that is simply by having many molecules in the interaction region. That's hard to do with nanocrystals or proteins, but if you're looking at small molecules, that's completely doable. And so in a way, almost easier experiment to do, or actually I would argue easier experiment to do, is to look at chemical dynamics of small molecules. And so the first experiment that we were part of was in 2014. So this has been done now for some time. And basically the setup is a regular pump probe setup. So you have an optical laser that photoexcites your sample. These are gas phase experiments. And then you have a hard X-ray probe that scatters, and the scattering is collected on a detector and provides in the first approximation structural information about the sample. And as you do that in a pump probe fashion, you see the structural evolution of the system. Now, there are a few points to note about this. First of all, we are in the gas phase, so there's no crystal and obviously no Bragg peaks, which relate to the crystalline lattice. And so you have a continuous signal. This is an actual experimental signal from DMP, one of the molecules that we looked at. And also because there's no lattice, it means that you're collecting all the scattering. So you're collecting both the elastic and inelastic scattering. And if you're energy integrating detector, which is something that I'll get to a bit later, it means that really you're collecting total scattering. Now, in the context of pushing towards attoseconds, so all the experiments that we've done so far have basically focused on structural dynamics. And actually, sorry, yeah, before getting to that, I did want to tell you a little bit more about the type of experiments on structural dynamics that have been done. Sorry, I'm getting ahead of myself. So in terms of the experiments that have been done, I want to just exemplify a little bit what is being done with these three experiments. So the first time resolved experiments that follow the chemical reaction looked at the ring opening reaction of this six-membered carbon ring, and it opens from cyclohexadiene, as the ring form, into hexatriene, which is the ring open form. And essentially the experiment is capable of following the nuclear wave packet, excited nuclear wave packet, as it ballistically sort of goes down these potential energy surfaces into either the ring form, the ring closed form. Another experiment that came a few years later looked at the less dramatic sort of chemical process, but simply at the structural dynamics of N-methylmorpholine, where the photoexcited molecule changes structure, and you can track the structure of the molecule in all its parameters, in all bond distances and bond lengths over time. Now, of course, saying that, we're tracking a nuclear wave packet. So the correct way to think about it is that we're representing the center of the nuclear wave packet as a function of time. For what I really want to speak to you about today, I think this experiment is very exciting. So this is still essentially a static experiment, but it managed to look at the effect of a transition from the ground electronic state into an excited electronic state. And so it goes from the ground state to the 3p Rydberg state. And that's quite a large change in the electronic structure, arguably. But the interesting thing is that one can see this change and resolve it in the experiments. I can really track the deformation. This is not structural dynamics. This is before any nuclear motion really has kicked in. And it's rather just about the deformation of the electrons in the molecule in response to photoabsorption. And so this gives us hope that in the future, given also the time resolution at extras pushing down towards sub-femtosecond, that one might really think about attosecond processes. So now more about where we really would like to go with this. So it'd be really neat if one could extend this type of techniques to not just follow the structural dynamics, but to really follow electron dynamics. So that would be, going back to Fernando's talk, the transient electron dynamics in the beginning, before you lose coherence when you photoexcite your system. It could also be the type of transient coherences you have when you cross a conical intersection. So for a brief moment in time, there'll be some electronic coherence, and that should give a transient wave packet, electronic wave packet that you could track. And in fact, Shoreham-Kamal has done some proof of principle calculations showing that this could in principle be observed. Equally, in a diatomic, you could imagine looking at avoided crossings and the dynamics of avoided crossings. We ourselves have looked at coherence between the ground and excited state in a diatomic as it vibrates in and out of coherence between the two electronic states. And we've also looked at, together with Ken Lopata in Louisiana, we've looked at ring currents in ring molecules when you kick out a K electron, but with no nuclear motion, admittedly. So this is all exciting, but I have to admit that everything on the slide is at this point fantasy or conjecture from theory, right? So experimentally we don't have anything, but how confident can we be about these theoretical ideas? Well, I wanted to just share with you sort of the state of art with the theoretical description of these type of scattering effects. And so actually, the earliest work on this type of scattering from electronic wave packets goes back quite a while. So Ken Wilson was quite visionary in the 90s, thinking about future X-ray sources. And so this is a slightly phenomenological paper, the top one, but actually it captures the essence of this type of scattering process. And then in the early 2000s, Niels Henriksen and Klaus Möller published a sequence of 3 papers that really derived the interaction from first principles. And I think they don't get enough credit for that work. It's quite elegant and I think important. And then in 2012, Robin Santra and colleagues, Gopal Dixit and Oriol Vendrell, simulated scattering from an electronic wave packet. Now, this is a wave packet you see here, and it's just composed of the 3D and 4F electronic states in the hydrogen atom. So it's sort of the simplest wave packet you can imagine, but it does, in the simulations, give an observable signal. And since then, there's been a lot of work by Robin and Gopal Dixit, Niels and Klaus, Shlomo Kamel, ourselves. Robbie Shaw has recently published a paper. And I think there's basically a consensus that this effect should be possible to observe in the future. We just need to basically push down the noise in the experiments and have sufficient time resolution to observe these things. Now, what does the basically theory say? Well, so you can start with an ansatz of the quantized X-ray field. We're not going to get into that, but basically you can describe the scattering in first order perturbation theory. So you have the interaction Hamiltonian, and you're looking at the scattering terms, the A2 term. Now, maybe it's worth saying that part of the reason that we don't suffer from radiation damage in these experiments that have now been done over the last 7-8 years is the fact that you see here at low X-ray intensity, to have radiation damage, that would be propagated to the photoionization term. And to have both photoionization and scattering, that's a second order process, right? So our damage process is a second order, and the low intensity, this is not a problem. And so if you go through the theory, you can come up with various expressions that describe the interaction. And this is one of them, which is taken in the limit of a semi energy resolving detector. So basically the energy detection window on the detector is crucial for what expression you end up having. But they all look relatively similar. And so you have here that the X-ray scattering cross-section, differential cross-section is related to the scattering from a free electron. And then you have a window function that relates to the energy resolution on said detector. You have the actual pulse. And then your material system comes in here. So we use a Born-Huang expansion, like Fernando elegantly showed in his talk this morning. And so you have the nuclear wave packets that in terms of electronic wave packets, will control your degree of coherence. And then you have the scattering matrix elements that bracket, so this electronic states bracketing the scattering operator. And if we think about the physics in this expression, there are basically this is the same expression shown on the previous slide. What we have are 3 processes. So the first 2 are well known. It's a coherent diffraction. Or people sometimes call coherent diffraction sloppily, but really elastic scattering, which is a Fourier transform of the 1 electron density of the state. And then you have inelastic scattering, which is a Fourier transform of the transition density between 2 different electronic states. And then finally, the term which no one has yet observed, but we hope to observe in the near future, is a coherent mixed term. And that's the one that bears a signature of an electronic wave packet. So here you have 2 electronic states that are populated, and it's in the interference between scattering from this state to this unoccupied state and scattering from this unoccupied state to this state that the actual information about the electronic wave packet is transmitted. I also would like to say that in terms of different limits, sometimes people don't quite like this picture, and there's a different picture in the limit of an energy integrating detector, which is just requires a bit more math, but you can then express the scattering as a Fourier transform of the pair distribution function of two electrons. And so maybe that's physically more intuitive to think about that, because literally you have a distribution of electrons in your molecule. The X-rays scatter from those electrons, and it's interference between scattering from pairs of electrons that gives you your pattern. And in an electronic wave packet, that pair distribution function will of course be time dependent. And so that's again what you're actually probing in your experiment. So we decided, at the moment we're trying to build up. We are theoreticians, but we always enjoy being very closely involved with experiments, and we're sort of building up towards experiments. And so we're trying to build our physical understanding of this coherent mixed scattering or scattering from electronic wave packets. And we decided to test our understanding by a toy model. So the Shin-Matthew model is really a 1D representation of a molecule, if you wish. So it has 3 nuclei, and in the calculations that I show you, the nuclei will be static. One can do calculations where the middle nucleus is actually mobile, and so have a degree of nuclear motion in the system. But for today, we're just having fixed nuclei, and then we have 2 electrons that can only move in 1 dimension, x and y. So x for electron 1 and y for electron 2. Now, because it's a system we can actually treat numerically, it's relatively straightforward to solve the time-dependent Schrödinger equation, and with the discretized continuum have a full range of states. And we can also, if we want to solve the time-dependent Schrödinger equation, either as just a superposition of states or numerically by, say, a split operator. And to show you a little bit what this system looks like, so this is the ground state. So the distribution here is the 1 electron distribution, which is the same one that's actually plotted here. So 1 electron sits more or less on this nucleus, and then 1 sits between these 2. And plotted in the x and y coordinates, you get these 2 blobs like that. And of course, you can calculate also the pair distribution function for this state, which then would relate to the scattering, if you wish. But how will then scattering show up in this, and what can we learn about scattering? Well, the first thing we wanted to look at was really how the static scattering, so without an electronic wave packet, will manifest itself. And we wanted to understand better the role of the continuum, or the continuum states in that static scattering. And so we looked at elastic scattering, which again is just a Fourier transform of the 1 electron density in elastic scattering. And now inelastic scattering is transitions between different electronic states. But if you have an energy integrating detector, you're looking at the total scattering, which accounts for all transitions. So in principle, you have to do a state-by-state calculation and sum it up. And that's a massive challenge. However, by resolution of identity in quantum mechanics, there's this very nice result that's been known for a long time that shows that actually you can reduce this to a double Fourier transform of the 2 electron density. And so actually already early in electronic structure theory, people were interested in this type of scattering. The experiments were not really done. There were extremely few examples of experiments that look at this, but in principle, total scattering is very closely related to electron correlation. So it's an interesting link. Now, in our toy model, we can actually do the scattering calculation, both the kind of easy way from the pair distribution of the electrons, and we can also do it state by state. And so we want to see what that teaches us about the physics of the scattering. And so what you see here in the beginning, please just look at the top figure. So what it shows is the static X-ray scattering from the electronic ground state of the system that we have. And so the curve, the blue curve here, is the total scattering. So it oscillates, and it goes from, you can easily show that at this is as a function of Q, which is the momentum transfer, by the way. So in forward scattering, the signal will be proportional to the number of electrons squared. And you have 2 electrons, and so very correctly, we have then 4 in the forward scattering. And then there are some oscillations that depend on the structure of the system. And then asymptotically, you end up with just having a signal as flat as the number of electrons in the system. So that's it goes to a limit of 2. We can also calculate the elastic scattering, which again has a limit of number of electrons squared in the forward direction. And then in the asymptotic direction, as you go to large momentum transfer, it goes to 0. So that all behaves as it should. So that is, let's say, a straightforward calculation anyone can do. But then what we can do now with this model is to actually sum up all the transitions individually. And so if we do that, we can first look at the inelastic contribution from transitions to other bound states, so from the electronic ground state to all other bound states in the system. And it turns out that the inelastic cross-section for all those transitions summed up is this blob here. Instead, the rest of the scattering signal, the total scattering signal, comes from interactions with the continuum, or rather transitions into the continuum, so corresponding essentially to single ionization. And the fact physically that this is the case for Compton scattering has, of course, been known for a long time. There's even a branch of spectroscopy at synchrotrons where people use Compton scattering to map the momentum distribution of bound electrons. So that in itself is not physically surprising. We know that this should be the case. But the fact that we can actually do the calculation the hard way is neat. So I think there's very few calculations like that out there. There's a really old calculation by Eisenbud in the hydrogen atom, where you can do this more or less analytically. And then Robin Santer and colleagues did a approximation in the carbon atom a few years ago. That's quite elegant with just using Hartree-Fock stator determinants. But really, there's not many examples of this out there. And then the lower graph just shows you that as you go from the ground state to a different electronic state, of course, this changes, and an excited state will have more structure. The distribution of the electrons is more complicated. And indeed, in that case, you have more structure in the signal. Nope. No. Oh yeah, there it is. We can also look at these individual matrix elements for inelastic transitions. And so what you see here on the left is the Q dependent, meaning dependent on the momentum transfer, and each inelastic scattering matrix elements squared. And so you see that when you have transitions to bound states, those are quite strong. So they have quite high amplitude, especially at small momentum transfer, which makes sense in terms of the momentum distribution in the bound states. And then these have been multiplied by a factor 10, and they are really the transitions into the continuum, into singly ionized states. And you can, of course, integrate them over Q to get the total scattering for each individual transition. And as expected from looking at this, you have quite a lot of structure depending on the distribution of electrons in the bound states. And then you settle into this kind of rather flat curve, which essentially correspond to a Rydberg series of electronic states, as much Rydberg as you can be in this model. And there is this one outlier here actually that caused us a concern initially, but it actually turned out to be a state that appears in this. This is again the electron density as a function of x and y, and you see the state, the transition before is to an electronic state that is kind of Rydberg-like, and the transition after is also again to a state that's Rydberg-like, has electron density out to the kind of far edges of our grid, but this particular state just happens to be more localized, and that's really what we're seeing. So everything kind of fits, but of course, really we want to then know what this means for calculations of electronic wave packets, and so we can form an electronic wave packet by simply superposing two electronic states. So we superimpose the first and the second excited electronic states in this model, And if you do that, you get a time-dependent scattering. That is, if you wish to, either a reflection of how the pair distribution changes with time, or an interference between the two different electronic states. And the signal is varying between these limits. So what we plotted here is the total scattering as the blue line in the middle. And then you see the upper line shows the coherent mixed scattering signal, the one that reflects the electronic wave packet at time tau A, which is when it's the biggest, if you wish. And then at tau B, when it's the smallest, or rather it's actually the same magnitude as the tau A, but opposite sign. And so the manifestation of the electronic wave packet is going to be a variation of the signal in the total scattering between those limits. So the shaded areas show you the variation that would be recorded, and that in principle then would give you information about your electronic wave packet. Now we can then proceed, because what we're then curious to know, so that the calculation I just showed you was done with total scattering, so accounting for all transitions implicitly. But now, because we can do this division into actually calculating the same thing as a sum over all possible transitions in the system, we find how a truncation of that sum, what kind of effect it has on the predicted signal. And so the correct signal, if you wish, the coherent mixed signal, is shown here as this red dotted thick line. But then what happens if you have a minimal model? A minimal model means that you just have the two electronic, you just consider the two electronic states that you have interfering in the wave packet and nothing else. Well, so you do get a strong signal, because of course there's a lot of the distribution of the electrons that's associated with that. And so that's the black line here, but it's not the correct signal. And likewise, if you then account for all interferences from the two occupied states to all the bound states, you get this dashed yellow line, which again, it is a signal, but it's clearly not the correct signal. And it's only when you account for all possible transitions that you get the signal that you should have. And so this has an implication for all the previous theory that's been done on this that hasn't used total scattering or sum of all states, because it means that you predict the wrong signal. Now, mostly this means that the signal that you predict has the wrong magnitude. That's I guess you could say it's okay if you're doing proof of principle work. It certainly is not okay if you're trying to interpret experiments. But also one can show that sometimes it will lead you completely astray. So you can take this model, and rather than having a asymmetric model, you can arrange the nuclei so that it's a symmetric system. And now suddenly we have ungerade and gerade symmetry in the wave functions, in the electronic wave functions. And it happens so that the first excited and second excited states are of different symmetry. And you can easily show that the implicit inversion symmetry that you introduce into the system actually means that the signal is, it vanishes. There's no signature of the wave packet in your scattering. And that if you do the total scattering calculation, that's exactly what you see. There's a zero signal. But then if you take this kind of minimal model that just accounts for these two states, really, you get quite a strong signal. And likewise, if you are then more ambitious and you truncate it at transitions or interferences to all different bound states, then you get this dashed yellow line, which still isn't correct. And it's only when you account for the full continuum that you actually get the right prediction. And so clearly there are warnings here about what the signal is and how it should be calculated. So to wrap up, ultrafast X-ray scattering has, to some degree, already been demonstrated as a very useful technique to track molecular geometry as a function of time, structural dynamics. There are already experimental demonstrations that you can distinguish between multiple reaction paths. You can detect the change in electron density as a function of time. And clearly the information in this type of experiment goes beyond structure dynamics. So you can actually Phil Buxbaum and his group showed nicely how you can deduce vibrational frequencies. You can see to some degree electronic states. We have shown how you can map kinetics of the overall reaction in parallel with the structure dynamics. But of course, we want to push into the attosecond barrier or the attosecond regime. And here it is clear that one has to be careful in theoretical predictions. So the continuum must be included. You know, fortunately, we can do that via total scattering, so we don't need a full set of continuum wave functions for our molecules. And there are already tools in existence that we have developed who can do that ab initio. And that's going to be important for predicting and interpreting future experiments. In terms of this model system, we're not giving up on it. We still want to look at the effects of nuclear motion and see what happens when you dress the system by optical field. And certainly, I think in the not too distant future, we should be able to see electronic wave packets, so electron dynamics, maybe detect transient coherences, look at correlation effects and ring currents and so forth. And just the most important, I know Carla is standing up, but I really would be amiss to not acknowledge these two people. So normally, those who have seen my talks before, I usually acknowledge the whole group and all our fantastic collaborators, both on the theory side and experiments. But really, in this case, the work was really down to Carl Michael and Mats. So actually, I gave an Atto battle, so Atto Friday seminar 2 years ago. No, and he heard my talk, and then he had been working on this model for strong field phenomena. And so he reached out and said, look, can we do something on scattering? And that has really worked out really great. And Mats is a very deep thinker in terms of X-ray matter interactions. So them together really did all the work that I've shown you. And of course, Stephanie Graffe was extremely generous to lend Carl Michael to us. We are going to have some postdoc positions coming up, so I just want to flag that up and thank funding. Good, thank you very much.
Thank you. So thank you so much. Are there questions for us? We are going into the coffee break anyway, but let's go for a few questions, and we have something circulating there, the microphone.
You mentioned that you see total scattering if you look with an energy integrating detector.
Yeah.
Imagine we had an energy resolving detector that can say distinguish with few EV and therefore distinguish the different inelastic channels. How would that change the picture? Would that be something that would really allow you to see more?
Yeah, absolutely. So we are obviously thinking in that direction already. So we're working with Hasan Yavas, who's at LCLS, and building energy resolving detectors. The lowest hanging fruit maybe there is to look at, try to distinguish the more or less the elastic signal. And so the elastic signal is then giving you pure structural information on the system, and the entire inelastic signal that you can then nicely separate out. It has all the all the electronic effects in it, and so that would be the first thing to do. But you can then, of course, in principle, resolve individual transitions, like we calculated here. You know, Scholl, who's always very quick to try ideas, has a paper out that we showed that you could, in principle, do. It's almost like Raman spectroscopy information. You can kind of map the electronic states around your dynamics. So I think there's loads of very exciting possibilities with that. Yeah, good question. Thank you.
Very nice talk. I have a question that is more related to the experimental implementation of this.
Okay.
So I hope
I'll try.
So yeah, to produce the initial coherent superposition that I mean the wave packet you want to study, you need a very short pulse. So there will be attosecond pulses in place. There are already attosecond pulses in place. So you will do this in ionized molecules. Okay. But as you mentioned at the beginning of your talk, people were using UV to excite molecules, and also eventually, if the UV pulses are very short, you can also produce coherent superposition in neutron molecules. So, what is your view about reaching short enough UV pulses in combination with the X-rays you need for the diffraction with the appropriate time resolution?
Yeah, I mean that's a good question. I mean, basically, what you're asking is can you, with a slightly longer pulse, get enough coherence to see anything interesting? So I think the answer is that potentially around, for instance, quantum intersections where the system itself establishes a coherence. So you're not relying on the, I mean, yes, you introduce the initial coherence with the optical pulse, but then the system itself establishes coherence later on. I think that's maybe the thing that one can hope for there. Because otherwise the UV pulses, I mean, you know, they're already essentially bandwidth limited, and so there's not much to be done. And then, of course, you know, clearly people have been able to do very interesting physics and chemistry with ionized systems. So in terms of learning about electron correlation and the coupling between electron dynamics and nuclear motion, I think that can still be studied in ionized molecules.
Okay, so thank you so much, all. Let's close the session. There's coffee over there. We are starting the other section then a bit later. We wanted to start at 11, but it's 11, so we start at 11:15. Now, for those who haven't sent us your talk by email or haven't contacted the people in the conference with your talk, please do so ASAP to avoid delays. Brad and Lindsay are taking care of the AV. Can you raise your hands? So Brad is here, Lindsay is there. They're taking care of the AV today. We really need the talks on the local desktop to avoid technical issues like those we had at the beginning of the session. And please test your animation as well, because if they are not working, then you still have time to fix it and we can try to accommodate you. Okay, thank you. Check your animation, please. What's happened to this clicker? Because I was
had to today,
but the reason it's not plugged in. But what is the plug?
But does it work with the PDFs?
But because the plug was here.
I didn't see it.
Because people must have plug everything. I was looking for the plug during all the section.
So there was one plug in, but it didn't do it.
Yes.
I opened it. I was the one who opened it. And there were the batteries, but I couldn't find anything.
No, but it was not the battery, it's the plug of the clicker that has spread the batteries that has disappeared. Okay, this is mute. Please mute this, because otherwise everybody's going to see this. And stop the sharing.
So welcome back to the quantum battles. So I'm chairing this session. So the first speaker is Dejan Milosevic from the University of Sarajevo. So he's going to speak about, you can read the title. Okay, thank you.
Okay, thank you very much. First, I want to thank Carla for inviting me here to present this talk. Okay, so I will talk about two new effects in above-threshold ionization. One is Terahertz-Pulse-Assisted ATI, and the other is Photon Emission during ATI. More time is devoted to this Terahertz-Pulse-Assisted ATI. I will also consider high-order ATI, also non-dipole effect, and an experiment which is planned at Eli Alps. And the last part of the talk is this about photon emission during ATI. Okay, so we have interaction with the terahertz radiation, and this is from 0.3 to 10 terahertz. This is definition of this range of the terahertz radiation. So, you know, this is a hot topic for modern physics. I gave here a few references, review articles about this. So nowadays it's possible to obtain a terahertz field with a strength larger than 1 megavolt per centimeter. This is still much lower than the strength of the laser field. So terahertz pulse alone is not strong enough to induce a significant ionization. However, the wavelength of terahertz field is much longer than the wavelength of the laser field. So vector potential of these two fields can be comparable. You know, dynamic of strong field processes depend on the vector potential. So this means that terahertz pulse can significantly modify strong field processes. And a small digression, if you look at the pulse length, terahertz pulse has much longer length than the laser pulse. And terahertz field can be considered as constant during the laser pulse. So in this sense, terahertz pulse-assisted processes are similar to static electric field assisted processes. And one example is my paper with the late Professor Staras about static electric field assisted X-ray atom scattering. This was field letters many years ago. And what you can see here is the spectrum of the scattered X-ray. So if you don't have a static field, you don't have anything practically here. But the long plateau for high energy scattered X-ray appear if you add static field, which is only 2% of the laser field. So this was motivation for me that when a strong terahertz field appears, to try to consider how they assist strong laser field processes. And I started with the ATI. So what we have here is the laser field. This is sixth cycle. And we have a combination of the laser field and the terahertz field, which has time delay for delta t. Here is the time, and here is the vector. The main panel is the vector potential. So you see a vector potential of the laser field is this in the middle, this green line, only 6 optical cycle. But you see the terahertz field is much longer with some time delay in optical cycle, which is given here 50, 75, and so on. And you see that practically, for example, look at this curve 75 optical cycle. So this dotted red line, it is approximately maximum here, but it is approximately constant during the laser pulse. That's what I said, that this terahertz pulse can be considered as a static field. And another example, if you look at 120, so this is here is the maximum negative value. So this means for the time delay of 120 laser field optical cycle, we have a negative value of this parameter. Here they are scaled by the laser field vector potential amplitude, and they are approximately same here. Okay, now numerical result. I don't have enough time to present all theory, but it is a generalization of the improved SFA. Details are in this topical review. But inclusion of the terahertz field is optical letters. So what you can see on the left are direct electron, and on the right are rescattered electron. This is photoelectron spectra, and probability and energy is infodermotive energy of the laser field, photoelectron energy. So you see these black lines are in the absence of the terahertz field, so only laser field. So you see you have for direct electron cutoff at 2 UP, and for this scattered electron cutoff at 10 UP, which are well-known result in the absence of the terahertz pulse. If we add terahertz pulse with this time delay, you see that the spectrum go to the or just to smaller energy, and it go down. And the same happened with the rescattered electron. So the cutoff position moved to lower value. However, if we have a larger time delay, if you look at this scale now, the cutoff for direct electron can go up to 10 UPL, and also probability is much larger here. And the same thing happened with the scattered electron for 120. So this curve, so it's about 20 UPL. So it is, and also probability increased. If you look at previous picture, so this small value 75 could correspond to positive value of the vector potential amplitude of the terahertz pulse and 120 correspond to the negative value. So this is the main reason for this difference. So these are numerical calculations, and I tried to explain this using first the classical model. Again, in this optical lattice, this classical model is given. So for 120 time delay, you see the cutoff is really for direct electron. These are the blue line is go to 7, and for the scattered electrons almost to 20. So this is agree with the numerical calculation. But if you look at 70, you see here we have a again 7, which is not observed in a calculation. It is less than 1 in a calculation. So the classical model fail for this. And then I use the quantum model. This is saddle point method for direct electron. This is saddle point time, real part, and imaginary part. This was 6 cycles, so there are practically 4 dominant solutions which I separated. And you see for the laser, this is this one. And for different time delay, it behaves differently. If we want to explain what is going on, it is better to look at this picture. And in the presence of only laser field, you have this line here. If you have a 75, you see this is almost linear and shifted up. But if you have 120, what happens? So it is go down, it has parabolic shape. This means that the cutoff value is much larger and probability is larger. So this means that this quantum model with saddle point method explain a whole feature of the spectra. And it also can be applied to the scattered electron. This is another paper, Fizrevey. For the scattered electron, you have ionization and rescattering time, and they behave differently in the complex plane. But the dominant is this orbit, which give you the cutoff about 20 for this time delay. And now you see that with the change of time delay, cutoff position significantly change, which explain the numerical results. So practically changing time delay, this is a powerful control parameter. You completely change the spectrum. Okay, these are publications. These optic letters. Okay, I don't have time to look at all details, but I tried different field configurations and cesium and argon atom, this intensity, and then I went to longer wavelength and to higher intensity of the terahertz field, and got interesting effects. So I will show this later. And also for higher terahertz field strength, we should use non-dipole effect. So this is optical actress with Dino Habibovic, who is here. And the last one is this European Physical Journal Plus 2. But what I am showing, this experimental project. So I'm principal investigator for Eli Alf's project in Szegedin. They have this terahertz field of this strength, and I will show you some simulations. So the experiment is planned very soon to be done. Okay, these are results for a stronger terahertz pulse. So this green line here is for 10 megavolt per centimeter, and the wavelength of the laser is 3100. So this is very large ponderomotive energy, about 90 electron volt. And you see the cutoff here is above 60. So we practically have a 5 to 6 kilo electron volt electron energy. So in some future facilities with a stronger terahertz field, we can obtain interesting effects, much higher energy of the electrons. And also there is this peak here, which also can be explained. I will show this later. Okay, now if we go to stronger terahertz field, then we cannot use the dipole approximation. You know, the dipole approximation is characterized with this parameter beta 0, which is amplitude of the electron motion parallel to the field propagation. And if you calculate this for the laser field, in all our cases which we considered, it is less than 1, so we can use dipole approximation approximately for laser field. However, for terahertz field, if we go to 5, 10 megavolt per centimeter, then it can be beta 0 can be 100 or more. So this means that we cannot use dipole approximation. We need new theory, and this non-dipole theory is in this optical express published last year. Okay, here are just some results from this paper. You see, in the absence of the terahertz field, this upper left panel, only slight asymmetry appears. This is because the parameter beta 0 is close to 1, but less than 1. However, if we add the terahertz field of this strength, then some asymmetry appears. It is shifted to the left and to the up. And with further increase, you see in this lower right panel, 10 megavolt per centimeter, it is completely deformed and shifted to the right. So this is for linear polarized field, and the X is the polarization axis. So it's off the polarization axis. Okay, now if we look at the spectra, electron energy, some interesting effect appears. So this red line is for dipole effect. So you see this cutoff about 30, but if we go off the polarization axis, then dipole result is a lower blue line. Okay, change the shape, but practically it is negligible. However, if you include non-dipole effect, then off axis you see this green line, big peak here, and shifted to higher energy. So this is what we obtain with this non-dipole SFA. And this can be explained again with the saddle point method. So you see this red line is a dipole. We just go to here. But if we include non-dipole effect and 10 megavolt per centimeter, it goes down and has parabolic shape. So this it exactly show that why we have this strong enhancement. Saddle point method explain our numerical result. And some numerical result for so cutoff for the 0. That means in the absence of the terahertz field is about 10, and it is shifted up to 34.5 megavolt per centimeter. But you see these peaks here for lower energy. It's about 7. This black line about 7 UPL. How we can explain this? This is for the scattered electron. But if you look at the quantum orbits, which give you the cutoff at 5 UP, so it's here. This cutoff, this quantum orbit, if you follow it to the lower energy, it changes the shape. It has one peak. And this peak is exactly at 7 UPL. So this means that quantum orbit theory for the scattered electron can explain these peaks. And they are interesting because these are some low energy structure. So this means that low energy structure, which was analyzed in the past for the in the absence of terahertz pulse, appear with the terahertz pulse and shifted to much larger energy, because here it's 7 UPL correspond to, I don't know, 500 electron volt or something like this, depending on the wavelength. Okay, so this is experiment which I suggested at Eli, and they have this. This is practically their regime. I suggested to use this wavelength 1030. This is the laser which they have, which is 1 kilohertz laser. Control the time delay. They have the terahertz source, They focus this on some sample, for example, inner gas, it can be argon or any other. And they ordered now this time of flight spectrometer to in order to register these electrons. So this is what is going on. And this is the simulation of this experiment. So interesting in the day laser is 220 femtoseconds. So it's very long, 176 cycle long. But still, we have these effects. So this green line is the laser field, and the vector potential for the motive energy is about 10 electron volt. So you see that terahertz pulse is practically constant during the laser pulse. Numerical results, this simulation. So this is classical above, and you see below here, here is the cutoff at 2 UP, and now it is shifted to 9-10 UP. So this should be observed in experiment, and also here it should go to 20 UP. And so much larger energy, about 200 electron volts. Okay, so this is what is expected to be observed in experiment, I hope, by the end of the year. As conclusion for this is that so we nowadays have a strong terahertz field such that the vector potential amplitude of the terahertz and laser field are comparable. We have a time delay delta t, which is a powerful control parameter. So we can increase differentialization probability by orders of magnitude. We can also increase the cutoff energy by several times. Experiment can be done at Eli halves, and we can have a kilo electron volt electrons for larger value of the terahertz field strength. And if you include non-dipole effect, the probability is higher. And we have some extended and enhanced spectrum, which allows someone to better resolve the days of the low energy structure, like holographic structure and other things. Okay, so this was first part of my talk. The second part is somehow connected to this because, you know, laser field can be used to generate terahertz pulses. And I just reversed this scheme in the sense that we use terahertz pulse to modify processes in a strong laser field. And now I wanted to do what they usually do, to obtain terahertz pulses from the laser field. And I wanted to develop a theory for this because I was not satisfied what they have in the past. But on the way doing this, I found that we have in addition to the ATI process, when we with laser react to some atom, we emit some photoelectrons are emitted. They can rescatter. We have high order ATI. But what happens if we have a simultaneous emission of the electron and photon with the wave vector k, which is presented here on this slide? So I wanted to formulate the quantum theory of photon emission during ATI. This is a single-step process, and I found that probability of this process is many orders of magnitude higher than that of high harmonic generation. And I analyzed this for various laser fields. Okay, so I'll just briefly go this. We have arithmetic theory in standard way, some initials, some final states, some Hamiltonian, but I added to this Hamiltonian this term, which is interaction with the photon field, with the vector k. There are some creation and annihilation operators, dipole interaction, omega k is energy of these photons. So initial state, we have bound electron, we have 0 such photons. And in the final state, we have continuum electron and 1 such photon. Now we just follow the standard derivation of that matrix theory. We have this integral dipole matrix element, And then we use the strong field approximation. We approximate the initial state just with the bound state here, and the final state with the Volkov state here. So this is a S-matrix element for simultaneous emission of the electron with the momentum P, and the photon with the energy omega k and with polarization ek. So this is some integral similar to the standard SFA matrix element for ATI, except that we have this term here. Okay, now if we have T periodic field, then we standard go from S matrix to T matrix, and finally we obtain the rate here, and here is the energy conserving condition. Okay, but now we are interested in only in this photon, so we have to integrate over all electron momenta. So we have three-dimensional integral. If it is linearly polarized field, this polar integral gives you 2 pi. We can also replace the integral over the electron energy with the summation over the photons. So we have practically one sum, one integral over the angle theta, and we have this highly oscillatory integral which appear usually in SFA with the shift of the energy. Okay, now we calculate this, and what we got for different wavelengths. So the upper curve is for 400 nanometer. This is linearly polarized field, argon 2 times 10 to the 14. These are parameters. Now, if we increase the wavelength, then it is shifted to the left, a peak appear, and oscillations diminish. And for 1800, it is peak is here, and but important is that we have peaks. So I was expecting that we have everything on the left side, and we have only low energy photons, which will give you the terahertz radiation, but it is not what appear. We have a peak here, which can be part of the ponderomotive energy of the laser field. And the probability is much higher than that of high harmonic generation. So for the same parameters, I calculated this cyan line with the dots here. So it is a discrete spectrum multiplied by 1000. So you see this is much larger. So it's almost 4 or more orders of magnitude higher than the high harmonic emission rate. So it's one single step process, while high harmonic generation is 3-step process. So probability is much higher. Okay, and okay, some more calculations here. It's just shifted with it is very long wavelength here. But if you present in an electron volt here, it is 6 electron volt. And just oscillation appear if you have a shorter wavelength. If you increase intensity of the laser, then it go up for a few orders of magnitude and shift it to the lower energy. Okay, analyze many other situations. It's not finished yet, but for example, if I go to higher intensity, then saturation effect appear. Then I use barrier suppression ionization model to calculate for highly charged ion the barrier suppression intensity, and then calculated for this ionization potential and this barrier suppression intensity the probability of our process, and found that it's a decrease for highly charged ion and shift to the lower energy. But you see here intensity is 2.6 times 10 to the 14, not 10 to the 16, yeah, 2.6 times 10 to the 16. So much higher than other intensity. And the point is that we can have this photon emission. Okay, I'm close. Oh, okay. I will just show result for bichromatic field. So this is a linearly polarized, monochromatic, and bichromatic. It's increased by orders, 1 order of magnitude, shifted to higher energy. Okay, for a bicircular field, this field here, it is farther. You see that 2 orders of magnitude increase and shifted to higher energy, and analyze many different situations. And the most important is this for OTG field, which we have a further increased and shift to higher energy. So for observation of these effects, this is maybe the best combination of the field. And the conclusion for this, so we have here a spectrum is continuum, for harmonic gyration it is discrete. But this process is not coherent. This is a one-step process. So microscopic rate is much higher than that of high harmonic generation. And also we don't have this suppression, this the magnetic B cross B drift, because you know, for harmonic generation, this three-step process, so that one has to return back in order to recombine, and this V cross B magnetic field suppress this return of the electron. And I found that for counter-radiating bicircular and OTC field, the rate is increased by orders of magnitude. Okay, I finished with this. Thank you very much.
Thank you very much for this very interesting talk. So now I have time for questions. Yeah, Robert.
Thank you. I have two questions. To the first part, I was wondering if your electrons, 1 keV or so, have time to leave the focus of the terahertz field in the experiment. Or is this, did you think about this?
No, I haven't think about this. So, okay, I just suggested that if we, at Eli, they are planning to increase the strength of the terahertz field. In this case, I can obtain kilo electron volt electron energy, but I haven't considered what kind of detector.
But in your calculation, you always assume that the field is always present and it just phases out as with time. So the electrons cannot leave the focus, so to say. Right?
Yeah, but I think electron just ionize and they leave the focus and you detect them.
I think it will be a difference if they leave the focus when the terahertz pulse is still acting, so to say, or still on. So you should get different energy distributions for the electrons. I would assume.
Yeah, but okay, that's the point. Terahertz field influence of these electrons when they move out of the focus. Yes. That is taken into account. Okay. That's why they have larger energy. Because terahertz field do not ionize these electrons. It just can be calculated. Yeah, so it just electron is ionized by the laser field, and then terahertz field change its energy and distribution and everything.
And I have a simple question to the second part. Can you give me a simple mechanistic explanation how these photons are created? What is the mechanism that you create now these photons in during your ATI? A simple
okay, just you have a electron atom photon, and in this process why not additional photons are emitted? By now we usually think we have a laser and then electron go out, but I don't understand why nobody in the past considered the possibility that photons are created in the same process. It's energetically possible.
Sure. And what is the mechanism, so to say, in a simple picture?
No, okay, you have a strong laser field, you have many photons, and these photons can be divided to electron energy and to this new photon energy.
Okay.
That's the mechanism. That's.
Thank you.
We don't have too much time for questions, maybe one more. I saw several hands, but I don't know who raised the hand first. Well, you
Okay, the asymmetry that you introduced because of the non-dipole emission, right? So you had this nice momentum plot where one is fully symmetric, where there is no terahertz field, and when you have the terahertz field, the butterfly picture shifts to a certain angle. So I was wondering what determines this angle. Like, is it I assume the terahertz field has the same polarization direction as the laser field, but you introduce asymmetry at certain angle.
Non-dipole effect, and then you have a perpendicular to the polarization axis. So when you have strong field, then a non-dipole effect have this component perpendicular polarization axis, and that is why it shifted to the.
Okay. So is there a knob that you can tune, like perhaps the phase delay between terahertz and optical, so you can actually confirm?
Sorry.
Is that angle tunable?
Angle is just shifted in the polarization plane for some, and the angle, if it is 90 degrees, this means that it is in the polarization plane,
right.
And it is just shifted for 3, 5, depending on the field strength. If the field strength is
just the projection
field strength is larger, then it is shifted more.
Right. Okay. Thank you.
Okay.
Okay, thank you. I think we have to stop the discussion here. Let's thank
Okay.
again. And the next speaker is Manfred Lein, and the title is to be announced, apparently. That's 30 minutes.
Right.
What is the microphone?
The microphone I have.
You have you are looking for one. Maybe this.
Maybe this one.
Doesn't work.
Previously, I was taught to use that. Did you use that one?
Yeah, this one.
Okay. Yeah. Good. Okay, thank you very much. And most importantly, I want to thank the organizers and in particularly Carla for organizing this. I know it's a lot of work getting the money, organizing everything and arranging everything. I'm really very thankful that I'm allowed to be here to give a talk for this event. So I will actually talk about something that has a lot of overlap with the previous talk, because I will also talk about terahertz plus infrared fields. But this doesn't have a pointer. Let me see if this one has. Okay, I'll use this. Oh, this one bit I can. Good. So this is a joint theoretical experimental work that I'm showing you. The experiments have been done in Hamburg in the group of Ulrike Frühling, and the PhD student who did those experiments is Martin Ranke, and the theory for this project has been done in Hanover by our former PhD student Simon Brennecke, and this work has basically been finished like about half a year ago, and it's already published in this paper. So this is a rough outline. I'll talk a little bit about the basics of strong field ionization. Maybe it's good to remind you of a few basic things that maybe we have heard not so much about in the previous talks. Then I will show you our work, and what I focus on in this talk, as in contrast to the previous talk, is we will talk a lot about low energy electrons and even zero energy electrons. So I'm talking about photoelectrons with energies much less than 1 eV, not about electrons with kilo electron volts or something like that. So that distinguishes the work from the previous talk. Let me remind you a bit about strong field ionization. If we have a low frequency field, and usually we consider infrared fields and also, of course, terahertz fields as low frequency, then we can think of tunnel ionization. We have, in the simplest picture, one electron bound in a Coulomb-like potential, and then we add to that the laser field. We create a barrier so an electron can tunnel out. This is tunnel ionization, and then after the tunneling step, this free, let's say, unbound electron feels still the laser field and can be accelerated. And therefore, the electron will move on such oscillating trajectories. It's oscillating because the laser field changes sign. And then in some cases, this electron can return to the parent ion. That happens, for example, here on the green trajectory. But before we talk about that, let me show you one typical picture of a photoelectron momentum distribution that has been measured. So this is it's a slice through a three-dimensional momentum distribution shown in this work up here. So we have the laser, it's a linearly polarized laser field, polarized in the vertical direction. And these are the two momentum components, parallel and perpendicular. So we see several important structures here. We see these circular rings. These are the ATI rings. They are spaced by the photon energy. But in addition, we see other interference structures, which are nearly vertical interference patterns. And this is this has a spider-like shape, and we call it photoelectron holography, which has been discovered basically in this work here. So this is all about direct electrons with no rescattering. But if electrons return to the parent ion, like here, we can drive an electron back, and then it returns, something else can happen. For example, we can generate high harmonics, photons, or the electron can scatter elastically, and then we can generate high energy photoelectrons, because after scattering, the electron receives even more acceleration from the laser field. And if we have rescattering, then you see, in addition to the central part of the momentum distribution, which is what I've shown you before, we have these high energy electrons. So we have here these rings around a high energy plateau. Okay, and now I will talk a lot about low energy electrons. So let me remind you of some important milestones in the development of this area. Here in this 2009 paper, it was discovered that when you go to mid-infrared fields, so these are 2-micron wavelength fields, then suddenly in the photoelectron energy spectrum, this strong peak shows up here. It was later shown that there are actually several of these peaks. So this is called the low energy structure. And here we have the very low energy structures. And later it was realized that there is actually even a peak at such low energies that you call it the zero energy structure. But this is actually a different effect. It's whereas the one on the left is really generated by the laser field interacting with the atom. These zero energy electrons, they can be explained only if you take the detector setup into account, because basically what happens is this structure is due to Rydberg states of the atom ionized by the detector field, because in the detector, there's a static field that extracts your photoelectrons, but it can even ionize loosely bound electrons that have remained in the atom. Okay, and we will rediscover this later in the terahertz setup. But before that, let me remind you of an important thing in attosecond physics, the attosecond streak camera. Here it's shown for the case where you have an isolated attosecond pulse here in the center, which ionizes an atom by 1 photon ionization. If in addition you have infrared field, the red one here, with moderate strength, this will not cause additional ionization, but it will streak the photoelectron. So it will change the energy of the photoelectron up or down, depending on the relative delay between the XUV pulse and the infrared. So basically you can say, when you plot the electron energy as a function of delay, you will see a shape that is essentially the shape of the infrared pulse. So now, if you look at this question, this picture, you can ask the question, how large can this modulation be? So here, for example, you see we have a photoelectron peak about 70 electron volts. So this is where 1 photon ionization takes you. And we reduce it down to about 60 electron volts. And you can ask the question, can you streak so much that you will hit 0 here. And to my knowledge, there is no such work with isolated attosecond pulses that really can stop the electron and bring it back to 0 energy. There is a bit of work on attosecond pulse trains, but not with isolated attosecond pulses. And this is one motivation for this project that I'm showing you now. We're now looking at streaking with a terahertz field. The ionization, so what we do is we ionize xenon atoms, but it's now ionized with a near-infrared pulse, not with an attosecond pulse. So, and this one has quite standard parameters, 25 femtosecond pulse duration, and the photoelectrons are streaked with a terahertz field with these parameters. Well, this wavelength apparently is much longer than the infrared wavelength. So what I like to speak about is maybe a degree of temporal localization that you can speak about. You can say you can ask how long is the infrared pulse here compared to the wavelength of the terahertz. And in this setup, it's actually a factor of 50. So you can say that this wave packet that you generate with ionization is very short compared to the terahertz field. And so it's highly localized temporally. This is how the terahertz field is generated in the experiment. It's optical rectification in a crystal here. And this is how the terahertz field will actually look like. So it's a near single cycle terahertz field. This is the electric field as a function of time. You see that the wavelength is roughly 1 picosecond. And then, of course, it's also important to ask how the detection works. The experiment uses velocity map imaging. So here you can see that we have now 2 pulses. Now the near infrared is drawn in blue because it has much shorter wavelength than the terahertz, and the terahertz is plotted in red. Here we ionize, we have an extraction field that smashes the photoelectron upwards onto a detector plane where we measure where they measure the 2-dimensional images. And they look like this. So we see the ATI rings that you know about, I guess. And in addition, you see in the center, there's this very bright spot. This is a zoom in. And you see these energies are at very low energy, like in the milli-electron volt range. And this is what we call the 0 energy electrons. And just to make the naming clear, this innermost part I call the low energy electrons. And this yellow bright spot at 0, I call the 0 energy electrons. And now, okay, I should say this is the measurement without the terahertz field, only infrared. Now, if we streak this with the terahertz field, so what will happen is, for example, if you look at an ATI ring like this, the terahertz field will streak it up or down by some amount, delta P max, it's called here. And this is in the simplest possible picture, just minus the vector potential at the time when this wave packet was created. And this is the measurement. So, and you see this simple picture actually holds for the upper, for the outer ATI peaks. So these are ATI peaks streaked up and down as expected. But in the center, there's this low energy region. You see there's also a streaking trace here, but there's more complicated structures that we want to understand. And so we have to do theory. And one thing that we did is solving the time-dependent Schrödinger equation numerically. It's a 3-dimensional Schrödinger equation using a potential that is more or less available in the literature for the xenon atom. And this is the comparison between experiment and TDSE for the case without terahertz. This is just the infrared pulse. And you see the agreement is reasonable. This is the central part. but you already see there's one thing that is not reproduced by the TDSE, namely the bright yellow 0 electron spot is missing. Everything else looks reasonable in the TDSE. And now, because we want to understand something, TDSE is not enough, and we also need another model where we can learn some more interpretation from. That's why we also use a classical model. And so the question is, how should we do that? Of course, the infrared field prepares some initial wave packet. And our idea is that we do such a calculation, and from this short TDSE calculation, we learn what are the initial conditions for classical trajectories that will then move in the terahertz field, plus the ionic potential. Just following classical trajectories. So this is how the initial distribution looks like in velocity space. And important is, the following point is important. All this becomes interesting because there's one ATI peak that is exactly at the threshold. So without the terahertz field, part of it is bound, part of it is unbound. And now when you streak this, you can move things in and out of the bound region. Okay, so this is the classical model in a brief overview. And now I show you the comparison between all three things: experiment, TDSE, classical model. You see that there's in general a reasonable agreement. We see the streaking movement on all these pictures, but as I said before, the central yellow 0 energy structure is missing in the calculations. But okay, let's for the moment ignore that problem and look at those structures that we can actually reproduce. So for example, you see there is here some bright structure at non-zero energies, and this is reproduced quite well in the calculation. So let's look at those for a second. So if we have the classical model, we can use it to interpret and understand the result. And one way to do it is shown here. We have split the classical picture into different contributions. So the sum of these four will give you the total picture that I showed you before. And it's split according to the number of crossings of the trajectory with the polarization axis. So why does that make sense? If there is no Coulomb potential, then the electron will never cross the polarization axis, because initially it just moves out, and it just, even though there is the streaking on top of it, it will not be bent back and cross the axis. And this, if we only select those trajectories that don't cross the axis, we get this picture, which looks very much like a regular streaking trace. If we select only those trajectories that cross the polarization axis once, it means that they go out, but then they are brought back and move to the other side. It looks completely different. And you see, this will exactly reproduce this bright feature here in the middle that I showed you before. So what does it mean? It means that this structure is essentially due to Coulomb focusing, because the Coulomb potential brings the trajectory back. And in principle, you can have higher order effects also with 2 and more crossings, but they will be more complicated to understand, of course. So let's move on. And let me just show you one picture of the trajectories that we find in this simulation. So this is again on the left, a comparison between experiment and TDSE. This is now at one fixed delay between infrared and terahertz, and we plot the two-dimensional momentum, photoelectron momentum images. You see, for this delay, there's good agreement between theory and experiment, and now we can find out where do these different structures come from. And so, for example, let's look at maybe here case C, maybe it's more interesting. I don't have so much time, so let's focus on case C maybe. C is somewhere out here at far away from the polarization axis. And if we look at the trajectory that generates a signal there, it looks like that. Electron goes out, comes back, and it comes back relatively close to the parent ion, so it undergoes some rescattering by a relatively large angle, and therefore electron will move to the right, and that's why it will end up at this large PZ. The red dashed line here is actually the classical boundary of the rescattering region. So you can say this is the analog of the rescattering that we know from the strong field ionization. But you have to remember this is different now, because we generate the electron with the infrared field and we make it rescatter with the terahertz field. In that sense, it's different, and it also means that the energies are, of course, somewhere else compared to the infrared case, right? I mean, the absolute numbers of it, it's not like the 10 UP, it's somewhere else in the momentum plane. Okay, then let's come back to the zero energy electrons. Where do they come from? Well, of course, the speculation is that they might have an origin similar to the zero energy structure in the infrared only case, being due to detector field. So we could have Rydberg states that are ionized after the pulses are gone just by the detector field. But there's another thing we have to consider. It's not so trivial to characterize these terahertz pulses. If I go back, this is what was measured to be the terahertz pulse shape, but you have to be careful because we don't actually know what happens outside this interval. So it could well be that these terahertz fields have an extended tail, and probably they do have an extended tail, but it was not measured how this tail looks like in this experiment. We know this from earlier experiments. And so probably both has to be taken into account. But we can, the problem is we cannot put such a long pulse into the TDSE. So we have to do something else. We do, to figure this out, a two-dimensional classical simulation where we look at various effects. So for example, we just try what happens with a long pulse with a long extended tail. That would be this example. Or we look at the short pulse and add the detector field to it. That would be the second panel. None of this alone will do the job. We have to do both to reproduce the correct amount of zero energy electrons. Now, one problem is that basically we know where the zero energy electrons come from. They come from both detector field plus extended tail of the terahertz, but we cannot do that. We cannot include that in the TDSE. So what should we do? We set up a simple, well, actually, we don't set up a simple model. We just use a simple model that has been proposed by the group of Jan Michael Rost in Dresden. They have derived, under certain assumptions, that if after the end of your interactions, there is still a bound state population in Rydberg states, you can derive that roughly 2/3 of those Rydberg electrons will be ionized in the presence of a static detector field. So, and we can calculate the Rydberg population at the end of the pulse. We take this number and we say 2/3 of it will be ionized by the detector field. And then somehow, really, this model works extremely well. It's for, I don't understand why, but you see that the black curve is this simple estimate that I just described, and it is exactly on top of the calculation of long pulse plus detector of the classical model. So we can do this also for the TDSE. And well, the final result is actually what you should look at is here on the right side, we have the zero energy electrons. The gray curve is the experimental signal of zero energy electrons as a function of the time delay. That's the gray curve, and the simple model is where is it actually? It's the it's the dashed one. I forgot to write that here, right? The dashed one is where we add to the TDSE this simple 2/3 contribution. Okay, so we have to quite some nicely, I think, explained this experiment, and I just want to come to the conclusions. I remind you of the key points of this work. The terahertz field can enforce rescattering of low energy electrons. And so it's nice because we really have an isolated wave packet that can be brought back to the core. And so we really have a control over the rescattering. I mean, in the infrared usual fields, the control is limited. Here we have two different fields, so we have more control knobs. There's actually no attosecond physics here, I should also say. Everything is far away from attoseconds. And we rediscover a lot of things that we know from standard strong field ionization, but with more control. We have a very high degree of temporal localization of this electron wave packet when we compare it to the terahertz period, to the period of the control field. Some future perspectives. So what I think actually could be particularly interesting is the second point here. If you look at the time scales, the pulse length of the terahertz field is in the picosecond range. So the scales were something like -2 to +2 picoseconds or so. This is comparable to the time scales of nuclear motion in molecules. So I think one could do a lot of interesting physics because we have comparable time scales. We could control electron recapture in such systems maybe. And maybe this last point is also interesting. You know, usually people originally when they did streaking and also rabbit, there was a lot of discussion about measuring times, ionization times, and so on. That is one big motivation. I didn't speak about that at all. Basically, I essentially assumed that there's no time delay in the multiphoton ionization that generates the wave packet. But we could also maybe try to look at small shifts of the streaking traces that have to do with something analogous to Wigner times. That would be the last point. And yeah, with that, I hope I stayed in time, and I thank you very much for your attention. Thank you.
Thank you very much for this very nice and clear talk. So, Mark.
Yeah, very nice talk. Yes, very nice talk, Manfred. I'm not sure if I agree with your explanation on the zero energy electrons, in the sense that, I mean, when you're doing the experiment as you described, then in principle, I mean, whether you would see Rydberg electrons being ionized or not depends a lot on how you operate your detector. If you leave it on all the time, eventually you will see the field ionization, but it depends on whether you're gating or not. And the important thing to make is that, I mean, a long time ago, we've done velocity map imaging experiments where we've used a narrowband laser that we tuned just above the threshold, you know, 2 millivolts, 5 millivolts, and so on. And I mean, as you're describing in your talk, right, there is this point where trajectories that do not recross the axis cross over into trajectories that do cross over in the axis. Now, precisely in between, there's a category of electrons that will cross the axis at the detector, right? There's a whole ring of these that contribute there. So what we've seen in our experiment is that in this range of from 0 to a few tens of milli electron volts, you always see a central dot of signal, very intense. So this is, of course, in a regime where there are no Rydberg states, right? So we do know it's really from this refocusing by the Coulomb plus DC field.
Okay, you're saying that could be a focusing effect different from the Rydberg ionization. Yes, I think we have considered this in the paper, but it's already too long ago. But right, you're perfectly right. This could also generate a bright spot somewhere in the pictures.
How important is it to match to the ionization threshold the photon energy, the ladder of the ATI?
Well, I would say it's very important. To be honest, I'm also a bit puzzled about this because we were just working with the data that we got from them, and somehow we were wondering, was it just an accident that they had the peak exactly at the threshold? My interpretation was that maybe they just picked the most interesting data and gave it to us for analysis. But definitely if you change the parameters in the theory such that the ATI peak is somewhere else, then we don't see any of this. Oh.
It's a quick question, I think. A very nice talk, thank you. I was fascinated by your suggestion at the end that about electron recapture and dissociation. Mm-hmm. So this process would be quite close to, I guess, what you call dissociative recombination, just difference in electron energy, essentially. And in that context, the cross sections with different partial waves can make a big difference. So here, what is the angular momentum distribution in these Rydberg wave packets?
Actually, yeah. So, well, I mean, because it's ionized by a linearly polarized field, of course, everything has to be cylindrically symmetric around the axis. And then in terms of L quantum number contributions, I think that the dominant one was L equals 1.
Quite small.
Yeah, quite small.
Thank you.
Okay, let's thank Manfred again for the nice talk. The next speaker is Marco Ruberti, Imperial College. So he's going to speak about Bell test of quantum entanglement and photoionization.
Well, is this working? Okay.
This is working. Just to make a share.
Okay, but first of all, thank you for inviting me. It's a pleasure to be here to give this talk. And thank you for the introduction to Fernando. I'm gonna try to be brief on things that we already discussed this morning. So just a brief introduction. I'm gonna talk about quantum coherence and entanglement in ionization of atom and molecular systems, describe what kind of Bell tests we can do to detect this entanglement between photoelectron and the ion, and then go to the specific case of photoionization with circular polarized infrared visible pulses, and show a case where we can simulate the state and write a Bell inequality that gives rise to violation, so to detection of entanglement. So I'll be brief here. Of course, we know that we are all interested in attosecond dynamics, where coherent electronic motion takes place, and the time scale is much faster than the one of nuclear motion. And with attosecond pulse, we can populate coherent superposition of electronic states and give rise to dynamics that we are interested in. Why are we interested in this? Because if we ionize a molecule, for example, in this case, photoionization with X-ray pulses of glycine, we introduce some coherent dynamics in the system where the oscillating charge, where the charge oscillates and moves across the molecular skeleton, and we are all interested in generating this and probing it. For example, in this paper published last year in Science Advanced, this was probed by using X-ray, photoelectron spectroscopy, or absorption spectroscopy. Both methods probe these dynamics. And this dynamics is eventually damped by nuclear motion, as we all know. And this is kind of the goal of AttoChem. It's not is focused on electronic coherence. And so we want to produce this coherence, probe it, and achieve some means of controlling it. But the question is, do we get this coherence? Do we always get this coherence when we do an attosecond experiment, when we photoionize a molecule? Well, in general, it depends. The answer is it depends. When we ionize a state, let's assume we start from a molecule in the neutral ground state. We can we produce what we call a bipartite system. So we have the photoelectron that leaves the parent ion. These two systems will be, let's say, part of the whole system, and they will both interact and be correlated in a quantum way. And whether we have coherence or not, and whether we have ultrafast dynamics in the parent ion depends on whether we can write the whole wave function of the system as a separable ion times photoelectron state, or whether we cannot do that. So it's to simplify, if imagine you have two ionic states and one photoelectron continuum state only, then the wave function on the left, here, will be a separable product of a term that depends only on the parent ion degrees of freedom and the terms that describes the photoelectron. This is separable and you have full coherence in each of the two subsystems. While in this case, if each ionic state is attached to a different photoelectron continuum state, then we have a perfectly entangled state, and there is no way of separating something that depends only on the photoelectron and something that depends only on the ionic degrees of freedom. So there is no coherence within each of the two subsystems. So which situation do we produce when we perform these experiments? Well, it depends on the laser pulse we use, of course, and on the system. So if we do XUV or X-ray photoionization, clearly the bandwidth of the pulse we use is important. If we have large bandwidth, we can, of course, coherently populate many ionic states of the many electronic states of the parent ion. But if we do, for example, other types of ionization, for instance, multi-photoionizations, there are several processes that play a role in determining the coherence or the entanglement, which is not only directly ionizing different ionic states in the same continuum, but also we need to take into account the ion photoelectron coupling and dipole coupling between different ionic states driven by our laser field. So in general, I hope I convey to you that this quantum coherence and entanglement are these key concepts when we do attosecond sign with ultra short pulses in many electron systems. And given that we most likely have photoionization, we produce these two systems, parent ion and photoelectron, which are entanglement. Why is this interest? Because if we want to have coherent dynamics, we want to limit the entanglement, because these are two competing phenomena, of course. And also, we would like to introduce, hopefully, a full quantum information perspective on attoscience, which thus far is not fully explored. So how do we do that? So the most rigorous proof of entanglement is a Bell test, right? John Bell derived some Bell inequalities where he proves that, which can be used to prove quantum correlations. The simplest type of Bell inequality, well, I'm not going to pronounce the surnames, but is that one, CHSH type. So what does it require? It requires two non-commuting observables per each subsystem. So in the original like format where we have two photons, for example, so you have particle A and particle B, you have different, like Bob will measure particle A, Alice would measure particle B, and you have different sectings for the two detectors, which we refer to as A and A prime and B and B prime respectively. One can define correlation functions, which is the expectation value of the product of the two measurements. And one can compute this linear combination of correlation functions and the violation of the Bell inequality, so the proof of quantum correlations is where it happens when the value of this quantity S is greater than 2. So if there is any quantum correlation, S will be greater than 2. And if S is smaller or equal than 2, that could be explained with classical correlations. Also, this type of Bell inequality are based on usually dichotomic observables, so observables that adopt only two values. So in the case, the simplest case is the two values being +1 and -1. And in this case, for example, the value of the average of the expectation value of these two observables would be at the detector, the number of times you get plus, here there is a minus, sorry, there's a mistake, and divided by the total number of counts. Anyway, so it's not that, it's quite simple. So what do we do with the photoionized system? So in this case, we have photoelectron and ion. So different settings of detector. Well, in general, this can be generalized to different observables, right? You don't have particle A and particle B, they are not the same. One is a parent ion and one is a free electron. But we need to find these two non-commuting operators, both for the parent ion and the photoelectron, that allow us to write this Bell inequality. So in general, let's say Alice will take care of the photoelectron, Bob can think about the ion. So let's start with specifying one thing which is important, is that this entanglement between these two subsystems can generally be encoded between many different degrees of freedom that belong to each of these subsystems. The degree of freedom, I mean, can be, for example, the internal states, energy states of the ion, the angular momentum of the photoelectron, the spin of the photoelectron, the energy of the photoelectron. So there are several degrees of freedom. And if the entanglement is encoded only in the internal energy of the two subsystems, then there's no immediate Bell inequality, because we need two non-commuting observables. And for a free photoelectron, every most observables you can think of will commute to the kinetic energy, right? Free photoelectron, momentum, angular momentum, spin, they all commute with kinetic energy. Whatever you measure, combination of them will commute, no Bell inequality. So we need to find, first of all, if you want to write Bell inequality, a case in which this doesn't happen. And one of these cases is, for example, the case of strong field ionization by secretly polarized fields. This was studied by the group of Ovgas Minova almost 10 years ago now. And it was shown how that there is a key feature that is attractive for a Bell test in this case, is that given that the ionization of counter-rotating electrons is strongly favored, you have got what is called spin polarization. So the photoelectron beam will have some spin polarization. Why is this interesting? This is interesting because this inherently means that the ion photoelectron entanglement is, in this case, encoded in the spin degree of freedom of the photoelectron. And the spin degree of freedom of the photoelectron is also something that is quite, I'm not an experimentalist, but I think it's measurable, right? It's not incredibly difficult to measure, as it's demonstrated by the fact that the spin polarization, for example, in xenon atom, has been measured already 5 years ago by two different groups that used the mole polarimeter to measure the spin of the emitted photoelectrons. So you can measure this. So how do you write the Bell inequality? So first of all, we need to look at the structure of the parent ion that is produced by this process. So this is the full how the ion photoelectron state looks like in written with formulas, and this is the same with the scheme. So these are the two states, that the two energy levels that are populated. The ground state has fourfold degeneracy, and the first excited state has twofold degeneracy. The energy gap is relatively small, is around 0.2 electron volts. And the photoionization is such that for each specific state, there is a very specific orientation of the photoelectron spin. Also, the laser parameters are such that the populations of these three states is comparatively small with respect to these three. Let's assume that this is 0, then you'll have this energy level fully polarized with spin up, and this energy level 50% polarized with spin down. Of course, this is not the case, just a simplification. In general, we will calculate the full state. So what do we measure? So we can measure for the photoelectron. So Alice will measure the spin of the photoelectron along the propagation direction of the ionizing laser, and then can measure also the spin component along a perpendicular direction to it, say X. What about Bob? So Bob has got these two energy levels populated after photoionization. They're both p states, so there is no dipole transition connecting these two states. Bob needs to be able to perform operations on this state, and in order to do so, it would like to use dipole transitions, because magnetic dipole transition are too weak. So it would like to use electric dipole. So it will want to use the second excited stage, which is 30.48 eV above the ground state, and would like to perform some operations so that it can promote or not promote population to these states, and then detect the fluorescence that will result from this operation. Given that we need +1, -1 measurement, this would implement the scheme, because +1 could be we have transferred population to the S state, -1 can be we have not transferred the population. So how do we do this trick? So after we photoionize, we can apply coherent control pulses to the parent ion. Namely, we can apply securely polarized resonant laser to induce this transition, and linearly polarized resonant laser to induce this other transition. This creates basically two basically independent three-level systems, and completely excludes from the scheme these two states that are weakly populated anyway. So we've got two three-level systems with we can write the Hamiltonian, the Rabi frequency is everything. Three-level systems, we can solve it. We can then compute what the effective ionic operator looks like. So the scheme is, first we photoionize, then we apply these coherent control pulses, and then Bob will actually measure in the basis of ionic eigenstate, but its measurement will be, the result of its measurement will be this Q operator and not the simple P operator, which is in the basis of eigenstates. Also, we need to consider also what we actually measure in the laboratory. So let's assume that we don't detect some degree of freedom of one of the subsystems, for example, the photoelectron. We don't detect the angle of emission, we integrate over it. So in order, this means that we take the full density matrix of the system and we trace out the angular variables of the photoelectron. And we end up with this reduced density matrix of the whole system, which depends only on the photoelectron kinetic energy. If we also don't detect the photoelectrokinetic energy, we will do the same operation by integrating away the kinetic energy of the photoelectron and remaining with the density matrix that only depends on the internal states of the ion and the spin orientation of the photoelectron. Here it's important to calculate the state accurately, because these coherencies are not to be simplified by, let's say, perfect coherencies, which will be if this off-diagonal matrix element were just the product of the two coefficients. So one is to calculate the state accurately. So how do we calculate? And then once we have this, we have our Bell inequality. Here, when we write expectation value, of course, we mean the trace over that density matrix that I just showed you of the product of an operator for the ion that we calculated before, and 2 times the spin, because you want +1 - 1, the spin is 1/2, so we multiply by 2. And one get this density, this value of the Bell inequality. This is the value, which depends on the photoelectron kinetic energy, if we don't measure the angle of emission of the photoelectron. At this point, what do we have left to do? Of course, we want to find appropriate laser parameters so that this Bell inequality is as much violated as possible. We want to, given that we have dependence on the photoelectron kinetic energy, we want to post-select events in which there is a specific value of this measurable, so that again the Bell inequality is even more violated. And also we can still play with the parameters of the coherent laser operations we do on the parent ion to maximize the violation. Okay, just briefly, in order to calculate the state, of course, we calculate it numerically using ab initio independent B-spline ADC. And this is the result. So this is the result for the following laser parameters. So peak intensity, 510 to the 13 watt per centimeter squared. Orange light, 2 eV, very short pulse. Duration 6 femtosecond, 2 or 3 cycles. Very broad bandwidth. Right. So as a function of photoelectron energy, the population of each of the 6 ionic states, and as well the real and imaginary part of the coherencies that are relevant for our Bell inequality. We have everything to calculate the Bell inequality. First of all, we post-select energy, which means that we have to normalize the state at each energy, because we will count only the events at that specific energy, and that will be the events that we do because we calculate the Bell inequality at each specific photoelectron energy. And then we have our result. The result is, well, we can measure with different resolutions, of course, but let's say for most of the range where there is considerable photoelectron need, we obtain violations that are not incredible, but they're still robust, around 215. And then we can do the same. So still, oh, this is still M. Yes, okay. So here it's important to understand the behavior of the violation as a function of energy. And if we plot the spin polarization of each of the 2 channels as a function of energy, well, one can see that the oscillation of the violation is related to the oscillation of the spin polarization. So basically, the more spin polarization we have, the more violation and the more entanglement we get. This is much more clear for the angular dependence of the violation. So imagine, instead of ignoring the angle of emission and just measuring the photoelectron energy, one does the opposite. You ignore the photoelectron energy, so you integrate over all the energies, but you place your detector only at a specific angle, and then you move it and calculate the Bell inequality for each of your settings. Then you have a Bell inequality for each emission angle, and as you can see, the more spin polarization you get in your as a function of angle, the more violation you get in your Bell inequality. And now, and then of course you can do, you can basically measure everything of your photoelectron. So you measure the energy, the angle of emission, and the spin. And there you have like an angle and energy dependent Bell inequality. These are the 2 spin polarization that you get for the first excited state and the ground state. As expected, first state has spin polarization around, I mean, positive in this case, depending on the angle, closer to 80–90%, and the ground state negative. Again, depends on the angle, but it can reach 40–45%. This is the total spin polarization, but this is irrelevant, and this is what you get for your Bell inequality. So you get basically violations of the order of 245. So these are quite strong violations, depending on where you place your detector, basically. And especially if you place your detector at points where you have got quite important yield, you still can get quite important violations. So this is basically a guide to where to place the detector to get the the strongest violation. And now it's also important to know that the Bell inequality is optimized for each point, meaning the operators that need to be used, the operations that need to be done on the parent ion for each of these points are in principle different. So this complicates things, right? Because I mean, imagine there is a experimental error. You select a point, an operator that which would be great for this point, but you actually measure a nearby point, then everything is messed up. So let's check how stable this is with respect to which operator we use. And this is quite stable because this is a fixed Bell inequality. So in the Bell inequality that is optimized for a specific point, energy 8 and 90 degrees, so somewhere around here. And this is how it performs across every point in comparison to the respective optimized one. And as you can see, the deviations of result is below 4% for most points, meaning in practice, you can select the Bell inequality for a specific point and then apply it to the whole range, and it will still work. And okay, and I'm already at my conclusions. So we developed, I mean, I showed you that we developed theoretically and simulated numerically the Bell test for proving the photoelectron entanglement. This will be the first Bell test applied to photoionized systems. We demonstrated robust violation of this Bell inequality for the case, in this case of noble gas atom argon, photoionized by ultra short infrared pulses in the strong field regime. Of course, here I wanted to emphasize, I mean, there is a button that says how quantum is Atto, where we are talking about Bell test quantum entanglement. So my answer will be a lot, because photoionization can be also an experimental test bed for quantum information in open multipartite quantum systems. And then as a vision, can we harness this concept, entanglement and coherence, as this is our whole hope, of course, to develop control strategies of chemical reactivity by acting on the photoelectron degree of freedom on the attosecond time scale. And with this, I would like to thank you for your attention.
Thank you, Marco, for this interesting talk. So, other questions? Yeah.
Marco, thanks a lot for a beautiful talk. So I have a question, comment, the following. So I was thinking about, remember in Bell experiment, they would change the Alice and Bob would locally change the angle of polarization of a photon, and they had to do a set of 4 measurements like this. And I was thinking in the same terms that, for example, in your ion, you have a 3-level system. So 2-level system maps into spin 1/2, 3-level system maps into spin 1, which means that dynamics in your 3-level system in the ion can be described as a rotation over polarization, basically, because it's a spin 1. And then I was thinking to access, for example, now the electron, you could consider the rotation of the linear momentum of the electron, which can be addressed independently by using elliptically polarized light. With the elliptically polarized light, you can change the, like an Atto clock, you can induce different rotations of the momentum. And then that would be kind of measurement on the electron, and the transitions in the ion would be measurement on the ion. So it's like a question, comment, in a sense that, do you think it would be intuitive to put your considerations and formulas into a picture in which you are doing a measurement in which you change the angles precisely like in the Bell measurement, like operating these angles? Because I think it's equivalent. It's just a matter of rewriting it.
You mean mathematically equivalent?
Yes, mathematically,
yes,
of course.
yes. I
That's
think that
important,
could make sense. Yeah,
mathematically equivalent.
yeah. I think so. I mean, I would need to have a look at it, but yeah.
It make it a lot more transparent and also understandable for people outside of our community.
Thank you. Yes.
You saw for high spin polarization, you had high levels of entanglement, but in terms of the fine structure splitting, is there an optimal value of the fine structure splitting between the two channels?
Yes, yes.
Because obviously, if it's too high, you have too high splitting, then one channel will
Yeah,
dominate, and if
it's
too low-
dominant and there is no entanglement.
So
Yes.
yeah. So is there a kind of an optimal?
Yeah, well, I mean, if so, let's say for neon would be even better because there is even lower splitting. Krypton would be worse, more splitting, but you can still reach strong violation. Maybe you need to play also with the laser parameters as well there. So because of course the energy gap dictates which one is most ionized, but also playing the laser intensity can a bit counterbalance this effect. So it depends. But yes, you want both levels to have a reasonably comparable population.
But not too small, I guess, because otherwise you don't get the spin polarization.
Well, the spin polarization is channel resolved, so it's an energy level resolved. So even if they have small gap, each can be, it depends. It becomes more difficult than to maybe for an experimentalist to play with this very small gap. I don't. Could be, yes.
Yeah. Okay. Thank you.
So I think we can move to the next talk. Thank you, Marco, again for the talk. And the last
this invitation to say something about work done over the past few years with the R matrix with time dependence codes on ultrafast atomic dynamics. And in this particular presentation, I'm particularly focused on some of the recent extensions to the code, in particular our capability to describe general laser fields beyond linear polarization. Which one is the? Is there a third one?
There was, but strange because this one should be working, but
That's the one that.
is it? Is it? Use this guy.
Okay, so we really want to use the codes primarily to study fundamental processes in ultrafast physics. And so we're looking at time delays in atomic photoionization. And we've also seen that it's now also possible to measure sub-attosecond time delays in molecular photoionization. And really these attosecond time delays are related to the atomic physics that is occurring within the atom due to the laser, in part due to the laser field. And really the strength of the R matrix approach is really to just get an accurate description of the atomic physics. So that is really what we're focusing on. And this ultra-fast dynamics might then manifest itself in various areas of physics, such as harmonic generation, but then also in molecules, we've got the charge migration. So we really want to focus and look at the fundamental changes in atomic dynamics that happen due to the laser field. And so it's important for us to start with an accurate description of the atom itself, because only if we've got that accurate description can we really start to look at the dynamics that is occurring. And so we built on the codes that have been developed in Belfast and also here at UCL over the last 50 years. The atomic R matrix codes are one of the most sophisticated codes available for the description of atomic scattering processes. It's also been combined with spin orbit codes, also with Dirac codes. And really there's current ongoing work to really look at these super heavy systems. So these are codes that really have been developed over a long time, really to get high quality atomic structure, high quality atomic dynamics. And what we've done over the last 15 years or so is really take that accurate atomic structure and transform that into a code suitable for dynamics. And from a Belfast perspective, that is really a change in really looking at the physics, because the traditional look of atomic physics is very much a static picture. Now it is actually a transition of taking these codes developed for static physics and move them into a dynamical regime. So the main principles are really to have a multi-electron atom where we include from the start the electron-electron repulsion in full detail. Then when we have these electron-electron interactions included, we then want to solve the time-dependent Schrödinger equation as accurately as possible. And the standard R matrix principle is to take space and separate it into two distinct regions. An inner region, where we use a basis set, which is really kind of a coupled channel basis to describe a residual ion plus another electron. And then we include some correlation orbitals to really get some of the important states described well. This additional electron that we need to use within this coupled channel basis is given by a semi-complete B-spline continuum, because we need to get an accurate representation all across this region. One of the difficulties of the calculations is that things get big. We don't make any assumption. We wanted to have strong fields. So we might need an angular momentum representation that actually scales up to about 100, which in the case of linearly polarized light means that we have about 200 symmetries in total. If you go to a full three-dimensional field or two-dimensional field, we go to something like 20,000 symmetries. It scales quadratically in L. So these calculations get really big, really quickly. We've got an outer region to describe the ionization of the system, and we allow a single electron to escape. And whereas in the inner region we use a basis set, in the outer region we use a grid to describe the wave functions. And so we have to make this transformation at the boundary from a basis set description to a grid representation. The grid representation is good in the outer region because we can ignore the exchange between the ejected electron and the electrons that are inside this box, because there are different regions of space, there's no overlap, we can ignore exchange. But the connection between the regions is something that we have to pay attention to. It is really where lots of problems in the calculations originate. In a standard R matrix approach, we have a connection through the regions, but through the R matrix. And what it really describes is a time in a standard R matrix approach, it describes a time-independent electron flow as a function of energy. And it is obtained by taking information from across the boundary, that describes the flow. Now, to take the outer region information and bring it to the inner region, we still use this R matrix approach. The only difference is that instead of having an energy here, we actually use an imaginary energy which is associated with the time step. To transfer information from the inner region to the outer region, we actually have a boundary region. And in this boundary region, we create a wave function from, on the grid using our basis set. And once we've got this grid representation of the wave function, we can then include it in the outer region calculation. And that allows us to transfer information outside. So by 2018, we had made pretty good progress with it, all for linear polarization. But we were able to get processes such as double photoionization described. We could go surprisingly far in mid-IR, 1800 nanometers, where we've got photoelectron distributions with the primary photoelectrons and also the rescattering rings that Manfred alluded to earlier. You can look at attosecond transient absorption spectroscopy and also XUV-initiated harmonic generation. But in order to go further, we really need to go beyond linearly polarized light fields. And so we've focused on that over the past few years, and we've been able to get vortex structures in the emitted electron spectra. We can use 2D light fields to look at spin change dynamics. We can also look at the production of spin polarized electrons. And it's also necessary if you want to describe molecular ionization processes, although I won't discuss that here. What I want to start by looking at is spin change dynamics. So if you have krypton and we look at a probe scheme, we can use a pump laser to take krypton from the ground state and excite one of the 4p electrons to the 5s state, and then subsequently excite one of the 4s electrons to the 4p shell to get an auto-ionizing resonance. And we can then monitor the population of these two auto-ionizing states, the singlet S state and the triplet S state, by varying the time delay between the pump pulse and the probe pulse. And depending on how we choose the polarization direction of this probe pulse, we actually excite the different states. If they are linear, we excite the singlet state. If they are perpendicularly polarized, we excite the triplet state. And so by choosing the angle of the polarization direction of the probe pulse, we can actually monitor this spin change dynamics and monitor the excitation into the triplet S state. So here are some results from a calculation where we have got the blue circles that indicate the excitation of the triplet state if you've got perpendicular polarization. The green line indicates the excitation of the singlet S state in the case of linearly, both parallel polarized. And we can also see this purple curve where we actually, if we just forget all about spin orbit dynamics. And so what we can see from here, first of all, is that it's absolutely critical to capture the dynamics here to actually have the capability to include spin orbit dynamics. We've got it in the codes, and for certain processes, it's going to be absolutely vital to include. If you don't include it, dynamics is going to be missed. We can also see that you can see this dynamics to excite the triplet state, but what you can also see is that it is more or less noiseless. It's a very smooth curve compared to the very wiggly curves in the case of no spin orbit dynamics or for the parallel polarization. And the nice thing here is that if we've got perpendicularly polarized pulses, we can only achieve excitation of the triplet state by taking one photon from the pump and one photon from the probe. we can't have 2 photons from the pump or 2 photons from the probe, because those can be parallel polarization. But if we have parallel polarization, we can have that process. And that interference leads to these ultra-fast oscillations in the signal. And so this spin change process is actually the cleanest, because it excludes some of these interference effects. So the previous slight change in topic, we had this code for general polarization. So one of the first questions was actually, okay, how good are we actually in describing multiphoton ionization using circularly polarized light? And we were at first very surprised to see this result of this change or this difference between the emission of co-rotating and counter-rotating electrons, until we looked at the literature in a bit more detail and found that this was already identified 8 years before we actually did the calculations. But we actually agreed extremely well with the findings from this paper, that really if you get to the ionization potential, which for fluorine minus is about 3 electron volt, at that point co- and counter-rotating electrons are equally likely to be ejected. Prior to that, counter-rotating electrons dominate above it, co-rotating electrons dominate. The findings were in superb agreement with the analytic theory. But if we take this a step further, we can also look at what happens if we actually have a very short circularly polarized pulse, and actually look at attoclock using circularly polarized pulses, but in a negative ion, so that we don't have any effects from the long-range Coulomb potential. And that should actually make the process cleaner, because we can really see in which directions electrons are being emitted. So initial calculations for fluorine minus were performed by groups in Florida and Iowa, and they used a 2-cycle circularly polarized field using a sin⁴ envelope at 1500 nanometer, using a model potential and effectively a single active electron approach, obtain these results essentially with 0 offset angle seen in the photoelectron distribution. Now, the RMT calculations, they use a full description of the system. And so what you do have in here is that the orbitals in fluorine minus are going to be very different from the orbitals in fluorine, in the residual ion. We can do Hartree-Fock calculations, where we use a Hartree-Fock description for fluorine, but we can also put additional configuration interaction in to get a good description of fluorine minus and really get these differences between F minus and F really articulated. But for these parameters, 1500 nanometers, 10 to the 13th, we get a relatively small offset angle. We get an offset angle of about -2 degrees, but it's still very small. If we then explore this in more detail and we go to a shorter wavelength, we go to 800 nanometers, we actually see an increase in these offset angles. So we've got co-rotating here, counter-rotating on the right, and we found a -9 degrees offset angle for counter-rotating electrons and a -6 degree angle for co-rotating electrons. You have to be a bit careful here because the atomic structure really comes into play. If you use the Hartree-Fock wave functions for the residual atom, we actually get larger offsets. We have to include additional CI, improve the description of fluorine minus and of fluorine, and then we suddenly see quite a notable decrease in these angles. If I'm not mistaken, the offset angles in the Hartree-Fock model might have been something in the order of 15 degrees, so quite a bit larger. So, going back to what Manfred just talked about, we can also look at spin polarization. And I can actually probably skip this. I mean, we had this kind of like, if you have this difference between co-rotating and counter-rotating electrons, you can get spin polarization. Was confirmed by measurement in xenon. But now we can also investigate what happens if we combine this with an attoclock principle. So again, we have the idea here is that ionization dominates in these channels where we've got doublet p3 halves, and we eject an electron initially with an m of -1. And this, the dominance of this channel leads to spin polarization with a theoretical maximum of -1/2. So what happens if we actually start to play with an attoclock as well? So we use larger pulses than what was described in the experiment. We use about 780 nanometers, and this was krypton. We go away from fully circular polarization. We go to slightly elliptic with an ellipticity coefficient of 0.87. And we can then take our final wave function and recast it in terms of co-rotating and emission of co-rotating electrons, emission of counter-rotating electrons. We can also describe it in terms of spin-up emission and spin-down emission. First of all, the co-rotating electrons are reduced by a factor of 7 compared to the counter-rotating electrons. But we can also see in this graph of the angular distribution of these electrons that there's quite a significant angular separation of about 18 degrees. So whereas we have a factor of 7 difference at about 110 degrees, if we look at about 150 degrees, we can see that we've got quite a pronounced dominance of counter-rotating electrons over co-rotating electrons, which is enhanced by this angular separation. So if we then use that as well to calculate or to separate the photoelectron spectrum into emission of spin-up and spin-down electrons, and then look at the spin polarization, we see this variation in the spin polarization with angle, where it varies around this average between a value of about minus 40% to about minus 28%. And so in specific angles, we can get a notable enhancement in the degree of spin polarization. Maximum enhancement about 20%. Right, the final topic, changing topic again. Another process that we've been looking at together with experiment at East China Normal University is rabbit with skewed fields. So instead of having, so we've got an attosecond pulse train and an IR field, but the IR field is now skewed in polarization angle compared to the pulse train. And we can see that this affects the sidebands in here. At 0 degrees, we get the standard sideband here in the middle. It's not the sideband that we're interested in actually, but it is the one that's most visible. But you can see at 55 degrees that this sideband is quite rotated. And at 90 degrees, it actually has a 4-fold structure. And so we can actually get more information about the rabbit process by actually looking at what happens as a function of skew angle between the XUV field and the IR field. We do need to be a bit careful here. 0 degrees and 90 degrees have a nice simple relationship between the magnetic quantum number of the outgoing electron and the magnetic quantum number of the residual ion. But at 55 degrees or at 20 degrees, that nice relationship is destroyed. So we do need to be a bit careful in the interpretation of experiment. But we can do the calculations and actually obtain very good agreement with experiment, although it's actually not as visible, unfortunately. in these pictures, but the sideband rings change in angle and they actually match really well between experiment and theory. And once we do that, we can then also look at these sidebands as a function of time delay, and we get the atomic phase shifts for the different skew angles, and again, get really nice agreement between experiment and theory. So we can really get this we can really get a high quality description of the experiment that's going on. And we can also provide really this, if we have this, we can also look at how do the different partial waves of the different, of the outgoing electrons, what are the parameters for these different partial waves? And so we can, I mean, within the R matrix calculations, the partial waves for the outgoing electron appear naturally, so we can easily extract them. Far more difficult in experiment. But if we actually look at that, here, these are just theoretical results. We can actually see how they actually change as a function of skew angle. So we've got m equals 0 and m equals 1 electrons for p electrons. We can also have f electrons in the sideband with m values ranging from 0 to 2, dark to light. They're the orange ones. But we can see that there's this difference across different angles or different skew angles between IR and HUV polarization. If we look at that in more detail, we can actually see that there are a couple of reasons why this might be happening. If you are in lowest order perturbation theory, you would actually expect these phases to be constant, but that's not the case. So here we've done calculations for different intensities of the IR field, from 10 to the 11 to 10 to the 12, 10 to 11 to 10 to the 12. And you can see that at 10 to the 11, almost all the phases are flat. Certainly, or if you look at the leftmost, so the column on the left and the column in the middle, you can see flat phases, which is consistent with lowest order perturbation theory at the lowest intensities. But as soon as we start to increase the intensity, things change. And that really indicates that we actually have to be careful with the intensity of the IR field in these rabbit calculations. Even at relatively weak fields, higher order effects can already be seen in the calculations. And so this was the case for neon, and we can also see changes occurring here in argon. If we look at the final phases that are obtained, we can also see that, yes, if we just look at specific residual ion states individually, we see constant phases. But if we start to combine these two, we get phases that start to change with behavior. So these varying phases are a consequence of two aspects. One is their connection to the different magnetic quantum numbers of the residual ion and the interference between these two. And the second is that one does need to be careful with the IR intensity. And this is to some extent an advantage of having a code like RMT, where it is really possible to look at these IR fields non-perturbatively. So we can really check the effect that the intensity has on the overall atomic structure. And that is important if you, especially if one wants to go into more detail and look in detail at resonance structures, where things like ponderomotive shifts of resonances start to come into play, and where it is really necessary to get good agreement with the experiment, both in terms of wavelength and intensity. And often theory has to be fitted to really get those parameters just right. The last thing that I want to mention is some recent work where we actually have taken these measurements at 0 degrees and 90 degrees and used kind of the angular momentum relationships that apply to actually separate the different pathways that lead to the same final state. So we can look at an outgoing p electron. But to start, if you have argon or neon, you start with a p electron, you end up with a p electron. But the two photon process can go to an intermediate s electron or an intermediate d electron. And by combining calculations and experiment at 0 and 90 degrees Q angle, you can actually start to separate these individual pathways and identify the magnitude and importance of each of these separate pathways. And so that's what's shown here is essentially a phase, atomic phase associated with the PSP pathway. And here we've got a PDP pathway phase. And we can separate these both in experiment and theory by taking two different measurements at 0 degree and 90 degrees Q angle. So what I hope to have demonstrated here is that by actually having the capability to look at basically electric fields with arbitrary polarization. I've really only presented 2D fields here, but in principle, there's no reason why we can't go to 3-dimensional electric fields. We can really use the RMT approach to illuminate new physics and to assist with the illumination of new physics. Agreement with experiment, we really started to get look at detailed agreement with experiment. And I think Linda has got some nice results to present on Friday on this as well. Really, the RMT calculations can really provide detailed support for experiment. But I also think that having kind of this capability to treat fields non-perturbatively is really useful, because it is sometimes important to check and verify that what is assumed to be perturbative is indeed perturbative. It's quite easy for things to become non-perturbative. So if anybody is interested in the RMT codes, they are available publicly. You can find references here, and they're also written up in this reference. Thank you very much for your attention.
Thank you very much, Hugo, for the nice talk. So now we have time for questions.
Thanks for the talk. So I have a question about the Atto clock and the rotation in the F- case. So you said you do see some rotation of the photoelectron spectra, where you don't, I mean, usually you don't see this in single active electron. So can you say for sure that this is like coming from electronic interactions? And also, like, have you checked which, like, is this just classical like electrostatic repulsion, or can you say it's coming from like some correlations or exchange or something?
It's very difficult to really pinpoint where things come from, because there are also questions like, is there an effect from depletion, for example? And that's also, I mean, it's very difficult. We did find that correlation clearly has a role, because there's quite a big difference between if we have kind of a very minimal description of fluorine, then we see kind of a very large or much larger offset angles than if we start to refine the description. So there may be correlation effects, but it's going to be very difficult to really pinpoint what might it be. I mean, that is sometimes difficult with these calculations, is really, yes, they might describe what might be happening, but getting a simple picture out of it is a completely different story.
I just wanted to make a comment on a simple picture. We looked at the spin resolved Atto clock in the past analytically, and what we noticed is that the offset angles that you show, they are very sensitive to intermediate resonances in each channel. So that, I would say, in my opinion, that would be the most important contribution. We also looked at the contribution of correlations, which one can, well, basically analytically, and these are less important from what we have seen. So what is also important factor that P plus and P minus electron, they trace a different trajectory. And this is also important contributor to the offset angle. And finally, if one considers the orbitals inside the ion, there is also phase accumulated with respect to different MJ channels. So these, I would say, would be the main contributors. And I would say that trajectory is the most important. Then the resonance is the most important if you're not in 800 nanometers. Trajectories are most important if you're in 900 nanometers. And the mix will be for everything. I just wanted to mention that this is indeed extremely important development that you're reporting, because it's very hard to calculate spin polarization for wavelengths in the like UV because of resonances, and because one really needs to know very accurately electronic structure. And the reason it's important because this spin polarization can be used in laser wave field acceleration for injecting, using strong field mechanism for injecting spin polarized electrons and then accelerating them. And people who want to model it, who want to do such experiments, they really need exact data as you can give them. It's really amazing. Thank you.
And I mean, getting the structure right is still not a trivial problem. And these.
Okay, I think it's time to close this session, go for lunch. So let's thank Hugo again.
Yeah. I would like to make a few announcements. The people who are joining the panel discussion this afternoon, if you would like to check your talks or everything, I would be grateful if you could do that now before you go for lunch. And I think please come here, and thank you all for joining. Okay.